I have to put the link on this. இப்போ நீங்கள் ஜாயின் பண்ணுங்க, அங்கேருந்து ஜாயின் பண்ணுங்க, இங்கேருந்து ஜாயின் பண்ணுங்க.
Just immediately close the YouTube.
This page, no? I just close.
Just close.
Okay, so here I have to go back to the my channels. Click on it. Oh. I have to go to video edit, right? Where do I go?
Go, yeah, the 3 dots.
No, it's just size.
Switch light.
No, here I cannot go.
Go to the video. There you will have it touch. There edit.
And I put the new link.
You're putting which link?
Today's link.
Why you put that channel live, na? It's in your WhatsApp.
Yeah, but
that if you put all 3 days, they can watch it from
okay, there. Okay, fine, I'll do that. Please sit, yeah. Where are you? Yes.
Someone decided Intel ID card and that this thing.
Is that the, we can take it later, no? What is the hurry? Well, you are a volunteer, you are supposed to come every day. You bunk your own duties, then what's Thiru, please admit people. Oh, I have not admitted you. Sorry. Yeah, admit, join here. No, first you let me make you host. Wait.
Recording in progress.
Okay, so echo. So, oh,
you mute.
I should leave. Okay.
Chico.
That's
Testing 1, 2, 3. Oh. Senpeng, can you hear me?
Yes, I can. Yes. Can you hear me or see me?
Yes, now we can.
Okay. Should I test?
Sorry,
Share?
we can't hear you very well yet, though. Maybe we could increase the volume a little.
Okay. Should I test to share my screen?
Yeah, why don't you try sharing your slides now and let's see how it goes.
How does it go?
Yeah, we can see it fine. Excellent.
Okay. 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 So I just stop at this slide. Okay.
Hang on a second. We still can't hear you very well. Can you raise the...
Raise my voice. How about this?
Yeah, that we can hear fine.
Okay. Okay.
But whatever was happening before was not loud enough to penetrate the hall very well.
Okay. So even now it is not well.
No, that's fine. Yeah, this is
Okay.
good. Yeah.
Okay. 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 Oh, I'll keep it in this position.
Yeah. I hope you're not hunched over in any weird way.
Yeah, for an hour.
Exactly. So you'll have, you should leave 5 minutes for questions at the end. So maybe I'll give you a warning when you have about 3 minutes left.
Okay, that's fine. So is this a 15 minutes talk plus 3 minutes of plus 5 minutes of question, or the 5 minute question included in the 15 minutes? I'm not sure.
Yeah, I'm not sure. I think probably 50 minutes and then,
Okay, okay, okay.
yeah.
I'll try to stop it.
If it goes a couple minutes late, though, it's easier than when when we only have half-hour slots, then people really need to end at 25 minutes after. But for the hour-long talk, if ending somewhere between 50 and 55 is good.
I see. Yeah, today is excursion day.
That's right. It's too bad you can't join us.
Yes, yeah, you know the COVID-19 here in Taiwan is still very serious. Yeah,
Uh-huh.
yeah, yeah. We are lag behind for 2 years compared to other countries. Yeah, because you know we are island. This is an island, so So everything, yeah, is lag, yeah, for a while, yeah, compared to other places world.
Yeah. Can you turn down my mic a little bit, please? Yeah, I'll keep talking so that you can tell us whether is that better, Olya? Yeah, okay. So I won't be talking most of the time, so. Sorry? Uh-huh. Yeah, right. So maybe we can turn off the ceiling lights, please. That clock is a little bit fast, so. Welcome everyone to day 3 of this fantastic conference. I hope you've all been enjoying it. The current session will be all online, so maybe some of you would have preferred to stay in your rooms the whole morning, but they told me I had to show up in person, so I'm glad you did too. Our first speaker of the morning is Senpeng Yu from the National Taiwan Normal University. He'll be giving us an invited 15-minute talk on sign statistics on permutations. Please go ahead.
Okay, thanks for the introduction and thanks for the organizers for the invitation. And today I would like to share with you the sign statistics on permutations from symmetric group to Coxeter groups. I'm Simpson Yu from National Taiwan University. The outline of this talk is that we'll give an overview of the framework and then introduction of some selected results in the 4 topics. The first is alternating permutations, snakes, and Euler identity. The second will be the Arnold families, Simpson, and the Andre permutations. And the third will be the sign Mahonian and sign Eulerian, Euler-Mahonian identities. And the fourth will be the sign counting over restricted subword. Then, after a very sketchy description on methods of proof, I will share with you some remarks and ideas. And let me here to thank all my co-authors. And a permutation statistic is a function, just a function from the symmetry group to the non-negative integers. So why do we start it? Well, you can say that permutation is a fundamental structure, and that's the reason But for me, well, that's for fun. And this is a very classic topic, so maybe it's somewhat a bit dated, but we believe that it is still worth to be mentioned. So over the symmetry group, there are three fundamental families of statistics, Mahonian, Eulerian, and Stirling. Let me briefly introduce them one by one. And Mahonian statistics, first we have inversion, which counts the number of pairs big, small, if it reads the permutation from left to right. Yeah. Then we have a measure which counts the sum of indexes where the values decreases. And a classical theorem of McMahon says that inversion and measure are equidistributed over the symmetry group. So we say a statistic is Mahonian if it is equidistributed with the inf. Then we have Eulerian statistics, first studied by Euler, the descent statistics, which count the number of places, there's a decrease. Then we have exceedance, which counts the number of places where the values are too big, bigger than the indexes. Then by the fundamental transformation of photon, you can prove that these two are equidistributed over the symmetry group. So we say a statistic is Eulerian if it is equidistributed with these two. The third family is the Stirling statistics. We have a cycle which count the number of cycles in the cycle notation. Then we have LR mean left to right minima, which counts the number of local minimas from left to right. And again, by the fundamental transformation of photon, you can prove that these two are equidistributed over symmetry group. Because the cycle counting is by the Stirling number of first kind, so we say that a statistic is Stirling if it is equidistributed with a cycle. Okay, now the point is that the symmetry group can be seen as a Coxa group or a reflection group, depending on what's your viewpoint. And we know that there's a full classification of finite Coxa groups, type A, type B, type D, and a bunch of exceptional types. And the symmetry group is exactly the type A. Or you can see it as a complex reflection groups, GRPN, and in this case, symmetry group is G11N, and type B is G21N, and type D is G22N. So it is natural to extend the result in symmetry group to these groups. Also, some statistics have unified definitions over the Coxa groups, for example, the inf. In Coxa group, there's a concept called the length. Length is the minimum number of generators needed to get the element. So in Coxa group, we define the length to be the inversion statistic because in type A, the value of inf exactly is the same with the value of length. Also, the descent in Coxa group, we have a unified definition of descent. We define descent is a cardinality of the descent set, which collects those generators by apply them to the elements, the length will decrease. Unfortunately or fortunately, for other statistics, there are no unified definitions. This makes the generalization interesting. And we have permutation models for type B, type D, and GR1N. For type B, the permutation models are the side permutations. You take ordinary permutation and you can put the negative signs on any letters. Then for type D, the negative letters, number of negative letters should be even. These are even side permutations, and these are the models of the type D. Coxa group. And the generating function for the type B and type D for the length generating functions are nice, very nice. But even so, if you want to read the length from the permutation model, this is not so easy. Yeah, there's some delicate formula here. And for the GR1N, the permutation models is the R-colored permutations. You take permutations of length n, and for each letter, you can color it in R colors. These are the color permutations and the combinatorial model for GR1N. But note that the generating function for the length is not R to R, 3R to NR. Okay, so based on these reasons, well, the direct generalization of the results in type A, well, sometimes it is not so trivial. So the framework is this. In the past 10 or 20 years, it is a paradigm to find the Cox version for classical results in combinatorics, and it was successful, very successful in some topics. For example, the Catalan combinatorics or the parking function and so on. So in permutations, the framework will look like this. You can take the Sn to Bn to Dn this road, or Sn to Bn to GR1n this road. So in the following, we will introduce some of them, all selected from some our recent or not recent work. The first topic is alternating permutations, snakes and Euler. This is a bit old, but I like this result, published in Advanced Applied Math. So an alternating permutation has a shape, zigzag shape, and they are counted by the Euler numbers, 1, 1, 1, 2, 5, 16, and so on. Back then, 250 years ago, Euler proved that the exceedance balance over the symmetry group result in the Euler number if n is odd. Then, after about 100 years later, Roselle completes the other half. He proves that exceedant balance over the fixed point free permutations, which means derangement, results in the Euler numbers up to a sign if n is even. So combine these two, we have a full picture. And these identities have a Q analog. It is done by Joshua Verger in 2010. Now, exceedance is replaced by the weak exceedance, and the Q counts the crossing number, which is the number of crossings if you draw the permutation in some certain way. And the result is a Q Euler numbers. Depends on the n is even or odd. We have a two set of identities. And the Q Euler number is defined by Han and Rajana Rivani and Zen in the form of continued fraction. So these are the background, and our goal is try to generalize these identities. So first of all, we need the concept of Euler number in other types. These are called the Springer numbers. And for Costa group, we take a subset of generators and look at those elements whose descent set is what we select, the J. Then the Springer number of W of the Costa group is the cardinality of the largest descent classes. And it happens that in type A, the largest set are exactly from the alternating permutations. So the type A Springer numbers are the Euler numbers. And for the type B and type D, we can also compute them. The type B Springer numbers are 1, 1, 3, 11, 57, and so on. And type D are 1, 1, 1, 5, 23. Let's just memorize them for a while. it will be useful. The second is that we need the concept of alternating permutations in other types. These are called snakes. So let's define three kinds of snakes on the side permutation. The Sn snakes has the zigzag shape. Then Sn0, yeah, we put another condition, the sigma 1 is positive. Then Sn00, we put another condition if the tail swings to the correct side. Now the Arnold and Joshua Verger proves that they have a nice counting. The Sn0 is counted by the type B Springer numbers, and the difference of Sn and Sn0 is counted by the type D Springer numbers, and the other two snakes is counted by the Euler number times power of 2. So that means Springer numbers have combinatorial models in snakes. So the last piece we need is to find a good statistics. It turned out that correct statistics for psi is the flag weak exceedance, which defined as this. And in fact, we are counting the balance of half of flag weak exceedance. So this is our result over the type B or type D permutations. If we count the balance of half of flag weak exceedance, then we got the number which counts Sn snakes. Okay. If we count over the fixed point free type B or type B permutations, then we got the Springer number of type B. If we counted on the difference of Bn minus the Bn star, then we got the type B or type D Springer numbers, depends on the parity of n. So this is our main results, but we can do more. We can have a Qt analog. In this case, T counts the number of negative entries, negative letters, and Q counts the crossing number, type B crossing number, and the balance result in the polynomial in T and Q. We call it R, T and Q, if we count over the type B permutations. Or if we count over the type D permutations, we have a similar result. Or if we count over the fixed point 3 type B permutations, then we got another polynomial which called QNTQ. Or if we count over the type D fixed point 3 permutations, we got another set of identity. And crossing, type B crossing, and the QR polynomial. Just a brief introduction. The type B crossing number is defined by Cotille, Joshua Verger, and Eulerian, which is a generalization of type A crossing numbers, yeah, in some certain way. And Q and R polynomial can be defined from some operators, and a theorem of Joshua Verger states that the generating function of Q and R can be written in the form of continued fraction. So this is end of the first topic, and I'm happy with this result because you know that there's not so many chances to generalize Euler's results directly, right? So that's the first topic. Then the second topic is about the Arnold family, and Simpson.
Sorry, can I ask a question?
Okay.
Could you go back to the crossing number definition? I just, you went too fast. Oh, for type A, sorry. I was wondering if, is it one of the Eulerian or Mahonian statistic? I just didn't follow the definition.
No, crossing is not Eulerian or Mahonian or anything. Yeah.
Okay. So it's you just draw the.
Yeah. I just draw the permutation in some certain way and count the crossing. Yeah.
Okay. Thanks.
Okay. Now the second topic, well, where is, okay, here. The Arnold family Simpson under permutation. This part will be proved later in Arnold Mathematical Journal. And now we know that in terms of alternating permutation, the snakes, we have an interpretation of the Springer numbers. But in type A, they are the Euler numbers. But there are other important permutation families counted by Euler numbers. For example, the Simpson permutations and Andre permutations. But most of their type B counterparts are missing. Yeah, so our goal is to fill the blanks. We need a checkpoint. This checkpoint is called integral numbers. The Euler number can be generated by Boustroff-Fedon triangle. Yeah, it will work like this way. We put a 1 here. Can you see the hand here? Yes, okay. Then we put 0 here, and 0 plus 1, we got 1. Then we put 0 here, and 0 plus 1, we got 1. And 1 plus 0, we got 1. And put 0 here. And again, we got 1, 2, 2. Then put 0 here. We got 2, 4, 5, 5, and so on. So these are called integral numbers. And the integral proves that they are exactly the number of alternating permutations of length n by the leading numbers. For example, the 0, 1, 2, 2 here is the number of alternating permutations of length 4, lead by 1, yes, no, and lead by 2, 3, and 4. So we have 0, 1, 2, 2. These are called integral numbers. Then we have Arnold numbers. Arnold extended Boustroff-Fedon algorithm to 2 triangles. We put 2, 1 here and do the same. But whenever we got a number at this edge, then we copy it to the other edge. Okay. And 1, 1, 2, and put 0, 1. We have 2 and 3, and copy the 3 here, and we got 4, 4, and then we got 11, copy 11 here, and we got 11, 14, and so on. So we have this table. The point is that the sum of each row will be the snake, the number of snake Sn, okay? And the sum of those entries with positive k will be the type B Springer number, and the sum of those with minus n minus index k will be the type D Springer numbers. So we call this number the Arnold numbers V and K. And Arnold and Joshua-Verger proves that these numbers just count the snakes or type B snakes or type B snakes according to the first element. So this is good. So this is our checkpoint if you want to define a reasonable Simpson or under permutations. So this is our result. We have assigned Simpson permutation of the first kind. Let us recall what is called a Simpson permutations. Simpson permutation is that for given k, for any k, fixed k, there's no double descent when you restrict the permutation to k, 1 to k. So this is not Simpson 3, 5, 4, 2, 1, 4, because if you choose k3, then we have 3, 2, 1. There is a double descent. But 2, 5, 1, 3, 4 is Simpson because for any k, well, you cannot find the double descent. So our result is that we can define signed Simpson permutation to be those signed permutation if the absolute value is Simpson. And if we put one more condition, we can define it as the type B Simpson permutation. And if we put yet one more condition, then we can define a type D. And the good thing is that the cardinality is correct and our checkpoint meets. If counted by the last entry, we result in Arnold triangle. So this seems to be a good definition of type B Simpson permutation. But we call it first kind because we find another set of Simpson permutation also seems reasonable. we call them the second kind. Now the signs Simpson permutation are those when restricted to minus k to k has no double descent. And after we put in some other conditions, then we can define them as a type B or type D. Again, the cardinalities are good, and by some nature statistics, we have entries in Arnold triangles. We found that these two sets of definition both seems to be reasonable, so we call them the first kind, second kind. Okay, but we can do more. Yeah. Hoffman studied polynomials, Pn and Qn, two families of polynomials defined by continuous differentiates the tangent or secant function and derive their generating function like this. And we can prove that we can refine each entry of Arnold triangles into polynomial such that the sum of the positive index of k will be the q polynomial, and the negative parts, the sum of them, will be the p minus q. This is good because, you know, if you recall the Arnold triangle, the sum of the left-hand side will be the type D Simpson Springer numbers. Okay, so these are the first few values of V and K, and now this is our final result. All the following. In fact, we have signed Simpson permutation of first kind and second kind and type B and type D. And also we have signed underlay permutations of the first kind and second kind and their type B and type D. All these 12 families can be refined to Arnold-Hoffman polynomials by some nature statistics. So this is our second topic. So, but well, there's some problems remains that because, you know, the Simpson permutation originally are from some connection with the geometry. So, so the next step will be to see that if there's any geometric interpretation or connection, okay, as well as the underlay permutation of both kinds. So the third part I would like to share is the signed Mahonian and signed Eulerian, signed Euler-Mahonian identities. Sorry. And this consists of two papers, both published last year, one in Journal of Algebraic Combinatorics, the others from European Journal of Combinatorics. And the whole thing started from a fantastic identity of Gassel-Simeon in 1992. They proved that the signed Mahonian, now the sign is controlled by the inf, and the Mahonian statistic, we take the measure. The signed Mahonian polynomial, over the symmetric group will result in a very beautiful form. The product of Q and log. But whenever you have an even number, you plug a minus Q instead of Q into the Q and log. Then Ardeen, Gass, and Reutemann considered type B case. And for the sign, they consider all the one-dimensional characters of type B. So there are 4 of them, and this one is trivial. So they consider all 3 other signs to be the sign Mahonian. And for the major, they consider the F major, Fpsac major, which is important, Fpsac major. Then they come up with the signed Mahonian identity for 3 cases. All have nice form. Okay. Oh no. Then for the signed Mahonian, for the colored permutations, in colored permutations there are 2R one-dimensional dimensional characters, and Caselli prove that they can be written in this way, indexed by epsilon and k. Epsilon will be minus or plus 1, and k is from 0 to up minus 1. And again, in the color permutations, there is a direct generalization of F major, and we call it the F major of color permutations. Then Biaggioli and Casati prove that they can have assigned Mahonian identity in this sense over the color permutations, and take the sign to be all characters, each characters, and Mahonian statistics F major. They come up with a nice identity. Okay, what do we do? First, we can write the characters, 2R characters, into another form. Now they are indexed by A from 0 or 1 and B from 0 to R minus 1. And we take another measure rather than F major. We take L major. Yeah, the reason is that L major is equidistributed with the length function in the color permutations, and Bagnall proves that they are equidistributed and with a generating function like this. So we give the sign Mahonian identity in this sense. We take Mahonian statistics to be the length or L major, and we consider all the possible one-dimensional dimensional characters, and we come up with a result identity in closed form. And also for type B, and the only non-trivial one-dimensional character is this guy. So we consider the sign Mahonian identity also in type D, and we also have a closed form. Yeah, but we can do better. And as said in the introduction part, except for inf and decent, for other statistics, we have no unified definitions in cluster groups. So from many contexts, you can have reasonable definitions for other statistics. So there are other reasonable Mahonian statistics on color permutations. For example, the following four are all equal distributed. F major, we have seen that. Then we have R major, we have F math, we have R inf. Yeah, all different defined from a different set of all different people. Yeah, so we can consider this form. Yeah, over the color permutation, we take one statistics to be the sign and take the second counted by Q, and our result is that all have nice identities, closed form, except for two. Yeah, these two we cannot find the closed form, but for others, we all have nice identities. Now we turn to Euler-Mahonian. Euler has a generating function of descent in this way, and Curtis considers its Q analog, then come up with a numerator like this. And so this is a joint distribution of descent and measure, and now it's called Euler-Mahonian distribution. And for the type A case, back in 1992, Desamelian and Flota proved this identity. I think the point, the spirit, is that it connected the left-hand side is the side counting over the structure S2n, a side counting, and the right-hand side is a normal counting. It's the normal counting. So Flota and Desamelian prove these identities, and then Vox proved a side Euler-Mahonian identity. Look like this: the side Euler-Mahonian identity over the S2n, and we result in a normal counting sine Mahonian, Euler-Mahonian, normal counting over the Sn, yeah, times a function. And for the type B case, Biaggioli give a sine Mahonian identity, yeah, in the same form. And we have, what we do is that we gave is signed Euler-Mahonian identity. It looks like this. The left-hand side is a signed Euler-Mahonian identity over the side permutation of length 2n. The right-hand side is the normal counting of sign Mahonian over the Bn times a function. And we can mimic the idea of Ardeen, Rahman, and Gessel. We put all the characters of type B in, and it turns out almost all we have identity. We have a close identity linking the signed version and the normal version. Yeah, it would look like this. Okay, but there are some well delicate point here. If you look closely, I'll omit that. Yeah, for example, this one. Well, the left-hand side descent and the right-hand side descent, they are different descent. Yeah, it's curious. Yeah, in a sense, but that's a very delicate point. Then for the type D, we also have the identity of the same form or similar form, I think. Yeah. And for the colored permutations, we have 3/3 of them. And except for the last line, the case GR1 to n plus 1 with the character indexed by chi1b, yeah, except for this case, we have a closed form as the theorem box shows. But for the last line, this case, just open, no conjecture yet. So this is a missing piece. So this is the end of the third topic. Yeah, I will proceed to the next one. So the side counting over the restrict subwords. Yeah, this consists of two papers. The first is from JCTA 2 years ago, and the next one is Advanced Implied Maths, published this year. And recall that the symmetric group can be generated by a bunch of generators where the SI is the adjacent transposition. Now we take the last K generators and we consider the parabolic subgroup generated by J. Then we consider the left parabolic quotient JW. Yeah, JW will be look like this. Yeah, it's nothing but a collection of those permutations which the largest K values will appear in this order if you read the permutation from left to right. That's all. And we denote it by a superscript n minus k plus 1 and n and bracket. And Humphrey proves that the inversion generating function over this set has a nice form. It's just a tail of the Q analog product Q analog of last k, last n minus k plus 1 numbers. Then the Stanley Forta and the Schuster-Berger, yeah, says that even in this set, the inf statistics and the major statistics are equal distributed. Then Caselli considered the sign, the Mahonian counting over this set, and he come up with a nice closed form will look like this. You can see that it's quite delicate. For example, the k plus 1, you should plug in minus 1, epsilon is minus 1, to the power of nk plus n plus k well into it. So this is quite delicate. Okay, now we take the first generators. Remember that in the last few slides, we take J as the last generator. Now we take the first K generators. Again, we can consider the left parabolic quotient. Then JW will look like this. It is a collection of those permutations. The first K numbers will appear in this order, and look at the sign Mahonian over this set of permutations. And this is our motivation, which comes from a conjecture of Caselli. He conjectures that if n is even or k is odd, then over these two sets, indexed by 1k and indexed by n minus k plus 1 to n, over these two sets of permutations, the sign Mahonian will be the same. So our goal is to develop a general theorem to explain this. So here is our result. We call it R versus R plus 2 theorem. Let R be a partial order among the numbers from 1 to n minus 2, and R plus 2 be the partial order among 3 to n by an increment of 2. Yeah, and Sn R superscript R collect those permutations whose index is consistent with all the relations in R. Yeah, let me give an example. Yeah, for example, if we took n is 5 and R, the relations like this, partial order 1 less than 3 and 2 less than 3, then R plus 2, yeah, is 3 less than 5 and 4 less than 5, just in increments by 2. Then S and R are those permutations in which 1 and 2 appear before 3. And S and R plus 2 are those permutations in which 3 and 4 appear before 5. So this is our main result. For an arbitrary partial order on n minus 2, we have the equality between the two sets of permutations. We count the side Euler-Mahonian, then the left-hand side is over SNR, the right-hand side is over SNR plus 2. So this is the result. So now we can give an explanation, interpretation, or reason why the Caselli's observation is true. Yeah, let us say that Sn1k, the sign Mahonian, is indexed by 1k. So because the R equivalent to R plus 2 theorem before, we know that the sign Mahonian polynomial indexed by 1k will be the same with the 3k plus 2, will be the same with that indexed by 5k plus 4, and so on. And again, the index by 2k plus 1 will be the same with that indexed by 4k plus 3, and so on. And we can prove that if k is even, these two polynomials are different. So that explains why n is odd and k is 0 fails, because when k is even, these two belongs to different families, because from this one there is impossible to shift to become this one. Yeah, for k is odd. Now for k is odd, the situation is better. Yeah, even we increment by 1, they are of the same. So when k is odd, all shifts are of the same. So this explains the Caselli's observation and confirm his conjecture. And the R versus R plus 2 theorem has some interesting applications. Yeah, we point out two here. The first one is a linear extension of an arbitrary pole set. Let P a pole set and let F be an injective labeling from P to n minus 2. And again, F plus 2 be the labeling by an increment of 2. So we consider the linear extension of both two labelings. The same pole set but two different labelings. So we have two sets of linear extensions. So the theorem says that for any partial order and any injective labeling, the sign Euler-Mahonian over the first set of permutation will be the same with the second set of permutations. So this is our first applications. And the second application is about pattern avoidance. Now we know that given pattern pi and a subset from 1 to n minus 2, and then we have s plus 2 is a subset from 3 to n. Now we define the AV and S pi, the avoidance, collect those permutations. The pi avoidance are only for the values in S. And AV Sn plus 2 are those permutations. The pi avoidance are only for values in S plus 2. Okay, again, this is for a single pattern pi, and for set of patterns, we define AV and SP and AV and S plus 2p similarly. The result is that let's P an arbitrary set of patterns and S be a subset from n minus 2. Then over these two sets of permutations, the AV and SP and AV and S plus 2p, the sign Euler-Mahonian counting are of the same. So, and for other types, the type B and type D and quarter permutations, yeah, I will only briefly mention this. The above on the restricted words can be extended to other types. And moreover, we can put all characters, the parity, the word restrictions, all these concepts into place. For example, yeah, if B and N are of the same parity, depends on N and K are of the same parity or not, we can have a signed Mahonian identity where the sign is the character, and Mahonian we take F major, and over the restricted words on the color permutations. Yeah, there are many theorems in this form. Yeah, so I omit it. So about the proof, I will say something, in fact nothing about the proof. Yeah, the proof in fact use very different techniques for each paper. And for the snakes, mainly we use continued fraction and lattice path model. And for the Arnold families, mainly we heavily use the tree structure from Joshua Verger and some bijection technique. And for the signed Euler-Mahonian or signed Mahonian, we use combinatorial arguments, the cancellation. And for the parabolic subgroup and words, for type A, yeah, we proceed by purely bijective approach. But for type B, D, and the color permutations, it seems that pure bijective approach is very, very difficult. And so we use generating function plus some combinatorial arguments. Yeah, this is all I can say about the proof. I'm sorry. And the last few minutes, I will try to share some remarks and ideas which I find them interesting. The first is called the folding phenomenon. And during the exploration, the following pattern emerges over and over. And let us call it the folding phenomenon. Yeah, basically, you take a structure of size 2n, then you do the sign counting. Yeah, you pick one statistic for the sign and pick another statistic for the Q. Then you got the normal counting, yeah, with respect to the second statistics. But now the counting will be doubled. And also the ground set will be the size n. And the result times a function, usually a rational function. For example, box identity, yeah, it's a typical. Yeah, over the signed permutation of type B of length 2n, you do the signed counting, signed Mahonian counting, then you got the normal counting over Bn, but now the F major should be doubled. and the result times a rational function. It's interesting that, in fact, we have more than 30 examples in this form. Yeah, we don't know why. Yeah, and not only over permutations, we have example in trees, in Catalan structures, and in tuple, in partitions. Yeah, so I don't know why this pattern emerges, not so frequently, but frequently. Yeah. So my question is that, is there anything lurking behind, or just a bunch of coincidences? Okay, this is the first comment. And the second idea I would like to share is the relative statistics. We can define the relative inversion of sigma with respect to pi. Yeah, this extends the k relative inversion of Gillespie and Kaliswski and Morse. And for the relative inversion, yeah, well, simply put, you just if you want to count the relative inversion of 132 with respect to 231, you just put 231 at the top and 132 at the bottom, and try to find a triangle in this way. And along this direction, yeah, the order follows. That's all. So in this case with 3, 3, 2, or in this case with 3, 2, 1. Okay, so if it satisfied one of these three inequalities, then we say we have a pi inversion. Okay, so the relative inversion of 132 with respect to 231 is 2. So now we can compute the relative inversion of each permutation with respect to other permutation. So this is a S3 case. So we have 6 new statistics, but if you look at closely, this column and this column, the relative inversion with respect to 1, 2, 3 and 1, 3, 2, well, they seems to be symmetric. We have 3, 2 here, and then we have 2, 3. Yeah, we have 1, 0, then we have 0, 1. But if you look at this column, these two columns, these are not symmetric. We have 2, 1, but we have, oh no, we have 2, 1, we have 1, 2. We have 3, 2, but we don't have a 2, 3. So these two are not symmetric. Our result says that inversion pi 1, inversion pi 2 is joint symmetric over symmetric group if there is an edge connecting these two permutations in the weak Burkhoff. And moreover, we can define the relative descent, relative measure, etc., and all inherit nice properties. But the question is that this is not if and only if. That means there are some symmetric case, but the permutations are not connected by an edge in the weak Burkhoff order. So the question is that if we can complete only if direction and generalize other types. Okay, the last one is the partial permutations. A partial permutation is a square 0, 1 matrix with some 0 rows or columns. And the last P and K be the size n by n, and with K 0 rows. It's easy to count the number of them. It will look like this. When K is 0, there's no 0 row. Well, we have an ordinary permutation. Simply put, a partial permutation is take a permutation matrix and delete some ones. And the point is that we can extend almost all classic statistics from ordinary permutation to partial permutation. For example, the inf and the RL min. You delete all the entry to the right and below of each one and count the remaining zeros, yeah, with certain restrictions. Then you got a result like this. Yeah, it's apparently a generalization of sturdy number first kind and the Q sturdy number first kind. And moreover, the P and K, the matrix counting matrix can be realized as Catalan matrix, which can be defined from two seeds and a recurrence relation. And it turns out the many results can be encoded in seeds. For example, the previous example, if we take C to be like this, then the Catalan matrix produced the entry is exactly the generating function with respect to area mean and weak exceedance inversion. I found this idea that everything is encoded in seeds. I found it quite interesting. And my question is that if we can extend this to type BD or other structures. And the last slide, more on side counting. In combinatorics, there are many nice theories involving side counting, the determinant, the hyperplane arrangement, the cyclic orientations, Ehrhart polynomials, and reciprocity, Möbius function, cyclic sieving or -1 phenomenon. That even pertaining to permutations here, there are still many missing pieces. So the question is that if we can fulfill the missing pieces and explore more, we believe that although this topic is classic, ancient, has a story, but we believe that there are much to be done. So permutation, my conclusion is that permutation statistics still have a lot of fun. Thank you very much. Thank you.
Are there any questions? Please raise your hand and somebody will bring you a mic.
Hi, that was an amazing talk. Thank you. You mentioned towards the end of your talk the Catalan matrix, and you asked if there's some sort of type BN analog for these things. I mean, I don't know if that's the question, but I just want to ask you if there is, do we understand a theory of orthogonal polynomials? Is there an analog of that for type BN somehow? Is there a way of, is there a different theory? If the classical theory of orthogonal polynomials is a type AN theory, is there something which could be considered a BN analog of that?
You mean the Catalan matrix or the parabolic part? I'm not so sure about your question.
No, all I'm saying is that many of the type AN identities, as you mentioned, are coming from this setting of orthogonal polynomials.
Yes,
right?
yes.
So is there something analogous to that which would give type BN identities?
I think so, but I didn't try it yet. Yeah, I think it's possible to do that. Yes, yes, but I didn't try it yet seriously. Sorry for that. Yeah, but I think it's possible. Okay.
Okay, I'll email you maybe. Yeah.
Okay.
Oh, yeah. The folding phenomena that you showed us that reminds me of the Stanbridge's Q equals -1 phenomena. Do you think there is any connection between them?
Yes, I think so. But I still cannot find a connection, a really deep connection of them. But in fact, it bugs me because the folding phenomenon, as I mentioned, we have more than 30, in fact, more than 50 identities in this form. But it seems to me so far that all these identities are independent. I mean, there's no relation between them. So I cannot see if there's something. Yeah, maybe they are just a tip of some iceberg, or maybe they are just coincidence. I don't know. I really don't know. But thank you for the question.
You mentioned these generalized inversions, inversion with respect to pi, relative inversions, you call them.
Yes.
So if I fix some pi, let's say of size 3, like 132 or something,
Yes.
do you have a nice formula for the number of or the generating function q to the inv 132 of pi for any pi for sigma in Sn?
Okay, that's a very good question. As we can see that, okay, they are here. Here it is.
Just a minute, it has not started sharing yet. I mean,
Yeah.
it's not sharing yet.
Okay, as you can see that fixed
Okay.
inversion, then we have a relative inversion, right? And
Yes.
Yes, and if there is a good generation function, some of them we have.
Yes.
Yeah, yeah, some of them we have. But if you want to consider the joint symmetric version, if we have a Qt bivariate generation function, then I must say the situation is very complicated. Yeah, for the n is 4, yeah, we have 12. No, we have 24. We have 24 relative inversions. So we have 576 pairs of joint symmetric version.
Yes.
And they can be classified into, I think, 14 or 6. I forgot. Yeah, they can be classified into several families. Some of them we can find the generation function, but some of them are still missing. Okay, this is all I
So
can.
they're of nice product form. I just
No,
the nice ones. Okay.
no,
Okay.
no.
Okay. I see.
Okay.
Okay. Thank you.
So I have a question. So some of these you count things, but can you refine by considering like set value statistics instead? Like instead of just looking at the number of descents, you can keep track of the set of descents, say.
Oh, yes. In fact, some of the paper I mentioned, we in fact have the set value version of the theorem, but I didn't show it. Yeah, because I think it will be too complicated. Okay, thank you.
Thanks.
So I have rather a comment. So if you are looking for symmetric joint distributions, I would like to advertise Feinstat. For example, there was a talk about Stirling statistics, and then the question arose whether there is a joint distribution for Euler-Mahonian Stirling statistics. And it takes about 5 minutes to code something to come up with such a pair, or actually a few pairs, triples, pairs of triples of statistics. So we also have this for sign permutations. For permutations, we have currently roughly 400 statistics in the database. For sign permutations, we only have something like 20. And it would be very nice to get this up to, say, 200 or 800. I don't know, depending on the sign. Many thanks. Sorry.
Yeah. Hi. So I wanted to ask if there are other type analogs for the Genoki numbers. I remember because you mentioned the Boustroff-Udron array and things. So I was wondering if there are other
yes,
type.
Yeah. Very good question. We are doing that now. Genoki numbers of type B. Yes.
Thank you.
Okay. Well, let's thank the speaker again.
Thank you very much, and thank you,
Oh.
Arvind. Yeah, thank you, Tom.
Thanks, Anpeng. And now we'll have to set up for the next talk. We have like minus 1 minute.
Dennis.
Sarah Browner, right?
Should I try to share my screen?
Yeah, please do.
Okay. Is that working?
Yeah, we can see it. That's great.
Let me see that.
So Sarah, do you want any warning before when you're at 25, before 25 minutes are up, or you'll
I guess. Yeah, sure. Yeah.
I can give you a 2-minute warning if you want.
Okay. Sounds good.
Okay, so our next speaker is Sarah Browner from the University of Minnesota. She'll be talking about a type B analog of the White House representation.
Yes, thank you. Thank you for the opportunity to talk. I'm sorry that I couldn't be here in person, but today I'm going to be talking about a type B analog of the White House representation. So the big idea of this talk is that I want to take some type A story that brings together combinatorics, topology, and representation theory, and I want to generalize that story to type B. Okay, so this is the precise type A story right here. And I don't expect you right now to understand what this picture is saying, but the goal of my talk is to explain this picture and then to tell you about my contribution, which is to generalize that picture to type B. Okay, so what I'm going to do is I'm going to first tell you about the symmetric group or type A representations that I'm interested in, called the Eulerian representations. And then I'm going to topologically interpret those representations, okay? And then I'll do the same thing over in type B. I'll tell you about the type B representations or hyperoctahedral representations that I'm interested in, and then I'll interpret those representations topologically. Okay, and so the story really begins with the symmetric group, and in particular, with a permutation, which I'm thinking about in one-line notation, and its descent set, which is the set of indices where I'm thinking of sigma I as bigger than sigma I plus 1. Okay, and so I claim that each descent set actually gives an integer composition of n, which I'm going to call the shape of sigma, okay? And I'll just show you how that works with an example. So here's my permutation of S in S5, and I can see that here 5 is bigger than 3, so that tells me I have a descent at position 2, and 4 is bigger than 2, which tells me I have a descent at position 4, okay? So the way that I get my integer composition is I draw a line after each descent, and then I look at the parts between each lines. So I'm shading them in here. This tells me that my composition is going to be 2, 2, 1, because I have a part of size 2, 2, and 1. Okay, so the statistic, it turns out, defines a subalgebra of the group algebra, the symmetric group, which is called Solomon's descent algebra after Solomon. And it's spanned by elements whose sums of elements with the same descent set, or equivalently the same shape. So for example, here's S3, the group in S3. Here are 4 possible integer compositions, and here are the corresponding elements of the descent algebra. So the important thing is if 2 permutations have the same shape, I have to take the sum of both of them. Okay, and so sort of the upshot here is that I have some combinatorially defined subalgebra of the group algebra that's indexed by compositions, or its basis is indexed by compositions of n. Okay, and so intuitively, when I want to understand an algebra, one thing that you can do is study its idempotence or elements E such that E squared is E. Okay, and so this was done by Garcia and Breitenauer. For the descent algebra, they defined a complete family of orthogonal idempotents, which I'm going to write as E lambda. So they're indexed by partitions of lambda. And I'm not going to define them because it's a little bit technical, but the idempotents that I'm interested in are going to be a coarsening of these idempotents. So they're called the Eulerian idempotents. And the way that I'm going to get them is by summing over these finer idempotents where the partition is a fixed length. So my idempotents will be indexed from 0 to n minus 1. For example, in n equals 5, here's how this coarsening works. So for example, this one with k is 2 is the sum of the 2 idempotents indexed by partitions of length 3. Okay, and so these Eulerian idempotents satisfy a really nice generating function, which was also proved by Garcia and Breitenauer. It looks like this. And if I were to expand this generating function out, in the case, for example, of S3, I would get these 3 elements of the descent algebra or the group algebra of Sn. Okay, so these are my 3 Eulerian idempotents in the case that n is 3. And I'm going to be thinking about representations of the symmetric group here. So to make sure that we're on the same page, I'm thinking about my irreducible representations as being indexed by partitions of n. And when I'm talking about an irreducible, I'm just going to write the Young diagram corresponding to that partition. And I'm going to use the fact that the symmetric group has really nice branching rules. So in particular, ways to restrict representations from Sn plus 1 to Sn. So the way it works is I take my partition, lambda, and I remove boxes in all possible ways so that I still get a partition. So for example, here, this is my representation of S3. If I want to restrict it to S2, I notice that I could remove this box, which would give me this partition, or I could remove this box, which would give me this partition. Okay, and so I take both of them. That's my restriction. Okay, so the symmetric group representations that I'm interested in are generated by these Eulerian idempots. I'm going to call them the Eulerian representations. And the way that I get them is by thinking about this idempotent, the ideal that this idempotent generates in the group algebra. So a nice special case of this is when k is 0. This is exactly describing Lie n, the multilinear component of the free Lie algebra. It's a very famous representation. And so let's see what these look like in the case of S3. We saw before that this k equals 2 idempotent here looks like this. So it's an unsigned sum of every element of S3, right? And so if I think about the ideal that it generates, if I multiply a permutation by this element, it's just going to rearrange the terms in my sum, but it's not going to change the idempotent. So in other words, the representation that I get is the trivial representation, which if you're familiar has a partition shape that looks like that. Okay, and the other two are a little bit harder to see, so I'm just going to tell you. The k equals 1 case is a sum that looks like this, and then the k equals 0 or Lie case turns out to be this irreducible. Okay, and so you might notice that altogether these give me the regular representation of S3, and that's going to be true in general. I'll get some sort of decomposition of the regular representation. Okay, so the property that I want to talk about today that these representations have is that even though I've defined them as representations of Sn, there's a way to encode or lift them to representations of Sn plus 1. So to formalize this, I'm going to say a representation V of Sn has a lift to Sn plus 1 if I have some Sn plus 1 representation, let's call it W, that restricts to V. So the way that I think about this is W has all the information that V has and then some additional information as well. Okay, and so a preview of what I'm going to say is the Eulerian representations have a lift. And so I'm not going to define it precisely, but I'm just going to tell you that this lift was discovered by Sarah Whitehouse. And she showed that these Eulerian representations, each of them for each k, they have a lift, which I'm going to write as Fk, and I'm going to call this the Whitehouse representation. So for example, here are S3 Eulerian representations. I want to think about what are the representations of S4 that restrict to these representations. So in the k equals 2 case, it turns out that the S4 representation is this, because if I remove this box, I get that partition, okay? The k equals 1 case looks like this, because I could remove this box to get that partition, or I could remove this box to get this partition, okay? And then the k equals 0 case turns out to be this. Okay, so these are my S4 Whitehouse representations. So just as a warning, that example was maybe a little bit simplistic, so it's not necessarily true that any representation can be lifted. So you could think about this representation here of S4 cannot lift to S5. And even if a representation does lift, it's not necessarily unique. So for example, this trivial representation of S1 could lift to this or to that representation of S2. Okay, so it's a sort of subtle property. All right, so to recap what I've said so far, I started with this combinatorially defined algebra called the descent algebra. And then I defined idempotents in that algebra. And I said those idempotents generate representations, and those representations have this interesting property that they lift from Sn to Sn plus 1 representations. But from what I've said so far, I've sort of given you very little intuition about why this lifting is happening in this case. And so that's what I want to do now. And the way I'm going to do that is using topology. Okay, so in particular, the topological space that I'm interested in is called the ordered configuration space of R to the D. So D here is the dimension of my Euclidean space. I'm going to write it like this. So I'm thinking of this as a set of n points. So each of these xi's lives in R to the D, and I'm just going to require that they're distinct. So for example, if D is 1, let's say I take n to be 3, it's just the set of points in R3 where each coordinate is distinct. I could draw this as a picture, right? It's going to be the complement of these 3 planes, which are the planes where 2 of my coordinates are the same. And maybe this picture is familiar, or if I project along this line where the planes intersect, I get this picture, which is the rank 2 braid arrangement. And in general, the D equals 1 case is going to be the complement of the braid arrangement. Okay, so a very natural question you could ask is, what is the cohomology of this space? And this has been answered by Arnold and Fred Cohen. So here's the presentation, and I don't want to dwell too much on what it looks like. I just want to note 3 things. So first of all, even though we're thinking about this for a general D, it turns out that the presentation only depends on the parity of D. So I'm going to get like an odd presentation and an even presentation. Okay. The next thing is that this cohomology ring, it turns out, only has n non-zero graded pieces. Okay, and then the last thing is that the symmetric group acts on this underlying topological space by permuting coordinates. And so that tells me that at the level of cohomology, I'm going to have an SN representation on this ring. Okay, and this actually gives us the sort of key connection between these 2 things that I've talked about. So the key connection here is that each Eulerian representation is isomorphic to, as a representation, to the graded pieces of this cohomology, this configuration space, in the case that I'm in this odd setting. So this was originally deduced by character comparison. So Phil Hanlon computed the characters of this side, and Sunderman Velker computed the characters of this side, and you can check that they're the same. I later proved this in the context of Coxeter groups. So this was the topic of my Fpsac 2021 talk. Okay, so here's an example for S3. This part of the picture is not new. We've seen this before. The sort of new part of this picture is that each of these representations here is describing the pieces of a cohomology ring. Okay, so we now have sort of 2 ways of thinking about our SN representations. You can ask, is there a way to understand the lifts of those representations, so the White House representations topologically? And so that's what I want to do next. And to do that, the idea here is I kind of want to add a point to the space R to the D. So that's going to give me a D sphere. And in particular, I want to think about the case when D is 3. So I have the 3 sphere, which is homeomorphic to SU2, which is the group of 2x2 matrices that have determinant 1. Okay, so we can take a configuration space or form the configuration space on SU2. And this n+1 here is telling you that somehow this is going to help me get my lifts. Okay, so this is a set of points, P1 through Pn+1. They're in SU2 and they're distinct. But now SU2 is going to act on this space diagonally by multiplication because it's a group. And so the space that I'm actually going to care about is the quotient by that diagonal action. Okay, so this might look like a sort of strange space, but if you think about a typical point, it helps. So here's a typical point if n+1 is 4. But because I'm quotienting by this diagonal action, I can multiply through by P4 inverse and get an equivalent point that has 1 as my last coordinate. And the idea is that I can do this in general. So a typical point in this space is going to be the set of points Q1 through Qn, where I'm going to require, okay, Qi is not equal to Qj is not equal to 1, and then 1 as my last coordinate. So intuitively, I can't draw a 3 sphere, but if we pretend we're in the 2 sphere case for a second, I'm just saying that I'm picking n distinct points on the sphere, and I'm not allowed to pick the North Pole. Okay. So the reason to study this space is that it has 2 very natural actions. One is by Sn+1. So this space is comprised of n+1 tuples, and I can permute the coordinates. Okay, so that gives me an Sn+1 action. But I can also think about the restricted action using this typical point, right? So I can just permute the first n coordinates and leave the last coordinate fixed. Okay. So I want to use this to relate this quotient space to the original configuration space that we started with, which we know is related to those Eulerian representations. And the way that I'm going to do this is via stereographic projection. So I was picking n points over here, not allowing the North Pole. I might as well stereographically project and pick n points over here. Okay, and so this actually defines a homeomorphism. So what I do is I take, I'm going to take a typical point here, and I will stereographically project the first n coordinates, okay? And then I'm going to forget the last coordinate, okay? And so I claim that this defines not just a homeomorphism, but an SN equivariant homeomorphism, because I can permute these points, and that's the same thing as permuting these points. Okay, so the upshot here is that this homeomorphism really tells us that this space is the right one to consider if we want to think about both an SN and an SN plus 1 action. So the SN action here is the same as the SN action on our original configuration space, but this quotient space makes clear an SN plus 1 action that was far from obvious on this original space. Okay, so when we move to the level of cohomology, functoriality is going to tell us that this SN representation carried on the pieces of this cohomology ring of the configuration space of R3 will lift to an SN plus 1 representation on this other configuration space cohomology. Okay, so we now have two different lifts, and you could ask, are these lifts equivalent? And the answer is yes. So this is work of Early and Reiner, who proved sort of exactly what you hope would be true is true. In other words, that this isomorphism of SN representations has a lift to SN plus 1 simultaneously. So these White House representations are exactly describing the graded pieces of this cohomology ring. Okay, so this is now gives us our complete type A story. Some other key features that I'm sort of sweeping under the rug is that there's a recursion that relates these Eulerian and White House representations. So one determines the other. And there's also on the topological side, some really beautiful connections to equivariant cohomology that sort of deepen this story. Okay, so this is the type A story. And what I want to do is generalize this to type B. So basically, I'm thinking of this as a signed version. So all of the type A objects that I've been thinking about, permutations, partitions, integer compositions, will become signed versions. So we'll have signed permutations as our group elements, signed partitions, and signed compositions. All right. Okay, and so to find a type B analog here, the first step is that I want to generalize this first part of my story where I started with the Eulerian representations and I lifted them to the White House representations. And really the first thing I have to do there is find a generalization of Solomon's descent algebra. And it turns out in this case that the right generalization is called the Montachi-Reinauer algebra. So it's a subalgebra of the group algebra of Bn. Again, it's combinatorially defined in a very similar way to the descent algebra, and this time it has a basis indexed by signed integer compositions, okay? So compositions that can be positive or negative. Again, we have orthogonal idempotence that decomposes this algebra. So this is due to Monica Vazirani, who showed that the Montachi-Reinauer algebra has these orthogonal idempotence indexed now by signed partitions, okay? And I'm going to do the analogous thing that we did in type A, that I'm going to coarsen these primitive idempotence by summing over certain ones. So in particular, I'm going to sum over the positive part of the partition that has a fixed length. Okay, so this is going to give me n plus 1 idempotence indexed from 0 to n. And what you should think is that these G lambdas are generalizing my E lambdas. And these GKs are exactly generalizing my Eulerian idempotence in type A. Okay, so again, I can think about the representations generated by these idempotence as the ideal that they generate in the group algebra, okay? And so a sort of preview theorem of what I'm going to say is that each Bn representation generated by these idempotence in the Montachi-Reinauer algebra has a lift to Bn plus 1. But really, to understand where those lifts are coming from, we have to turn to topology again. Okay, so this is the last thing I want to do is I want to find some sort of type B analog for this topological story I told you about the cohomology of this configuration space lifting to the cohomology of this sort of more complicated quotient configuration space. So when we move from type A to type B, the objects in type A were configuration spaces. Now we're going to think about Z2 orbit configuration spaces, which I'm going to define via an example. Okay, so the orbits we're thinking about here are Z2 orbits. So we're thinking about the action of Z2 on SU2, or the 3-sphere, via the antipodal action. So pictorially, this looks like sending, the North Pole to the South Pole. Algebraically, this is like sending P to negative P. Okay, and so I can define this Z2 orbit configuration space on SU2. It's the set of points P1 through Pn plus 1. They're all in SU2, and this time I'm going to require that Pi is not equal to plus or minus Pj. Okay, so that's where that orbit is coming in. And this n plus 1 is telling me somehow this will get at my lifted representations. So again, SU2 is going to act diagonally on the space, and I can quotient by that action. Okay, and I can again think about a typical point in my space as, okay, it's going to be Qi is not equal to plus or minus Qj is not equal to plus or minus 1. Okay, and then 1 as my last coordinate. Okay, so intuitively what I'm saying is, all right, I want to pick n points on the sphere. I'm not allowed to pick the North Pole. I'm not allowed to pick the South Pole. And if I pick a point, I can't also pick its antipode. Okay, so there's some more conditions, but it still makes sense. And again, we have these two very natural actions. So we have a full action of Bn plus 1 on the space, because the space is comprised of n plus 1 tuples. And then so now I'm going to permute and negate my coordinates. Okay. Or I could think about this restricted Bn action where I'm permuting and negating just the first n coordinates here. Okay. And leaving that last one fixed. Okay. And so I want to use this, this sort of the same idea that we saw in type A to obtain sort of a description of this quotient space as related to a genuine orbit configuration space, so not a quotient. And I'm going to do it in the same way via stereographic projection. So I have to be a little bit careful here. So in type A, I was saying, okay, remove the North Pole, which is fine when you stereographically project because that's what you do. Here, when I'm thinking about points in my space, I was saying I can't pick the North Pole or the South Pole. So what that ends up being under stereographic projection is that I can't have 0 in my set of allowable points. So that's not a big deal. What's a little bit more subtle is that we have to be careful about this antipodal action. So in SU2, the antipodal action was just sending P to negative P. But once I stereographically project, I get a weird scaling factor. So Q is going to go to negative Q over its magnitude squared. So I still have a Z2 action over here, but it's just a little bit strange. Okay, so nonetheless, we have sort of a parallel story. So this was the homeomorphism that we got in type A, relating this quotient configuration space to the configuration space of R3. And in type B, we get a very similar homeomorphism. So here is our quotient orbit configuration space. And I'm saying that it's homeomorphic to a Z2 orbit configuration space on R3, which I'm going to write like this. So this is a set of points P1 through Pn. Each of these PIs is in R3, but not 0. And they're distinct. And I also have that Pi is not equal to the image of Pj under that antipodal Z2 action. Okay, so to give you some intuition for this space, if you remember in type A, when D was 1, this configuration space was just the complement of the braid arrangement, right? In type B, this configuration space here is not the complement of hyperplanes anymore, even in the case that D is 1. So for example, this is what the n equals 2, D equals 1 space looks like. So you can see that I'm taking the complement of some lines, but then I'm also taking the complement of curves.
Sarah, can you take about 2 or 3 more minutes?
Yes.
Thanks.
All right. So the theorem here is that this topological space and these representations coming from the Montachi-Bernoulli algebra are exactly what we want. So first, we have an isomorphism of Bn representations. So these representations coming from the Montachi-Bernoulli algebra are exactly describing the Bn representations on the graded pieces of this cohomology ring. The second thing is that this Bn representation has a lift to Bn plus 1, where it's being described by the cohomology of this now quotient orbit configuration space. All right. And then we have analogous recursions that relate the sort of Bn representations with their lifted Bn plus 1 representations, and analogous connections to equivariant cohomology on the topological side. Okay, so in summary, here is our type A story, right? We started with representations coming from a combinatorial algebra. In type A, it was the descent algebra. And on the topological side, we had the representations on this configuration space cohomology. And then we said that those representations lifted to Bn plus 1. All right, and then in type B, we have these, our representations that are coming from a combinatorial algebra are coming from the Montachi-Reutenauer algebra. They're isomorphic to the representations on the cohomology of this orbit configuration space. And again, they lift to Bn plus 1. Okay, so this is sort of this lifting is a very subtle property. So I think a natural next question is to really understand where and when we get lifts, generally, especially in the context of Reith products. All right, thank you.
Thanks. Thanks for a beautiful talk. Any questions? Is there any hope of doing this in other types? I know the Reith product is a natural place to look, but you know, type D or something?
I think type D is also a reasonable hope. And sort of, I think we understand very little about this like lifting property. It's very subtle. And so I think like even in the symmetric group, we don't understand really when it happens. So I think that in general, like we could expect that there are representations of Dn that lift to Dn plus 1. Yeah.
Mm-hmm. Any other questions? Ah, sorry, Sheila.
Yeah, hi, Sarah.
Hi.
Hi. I just wondered, what made you think of doing it with Z2 orbits? Was that just a natural sort of thing?
So originally, when I was trying to generalize this picture, I started on this side and I was trying to find a lift of the Bn Eulerian representations, which wasn't working. And I think, I proved to myself that they couldn't lift. That was like an impossible task. And so then I sort of decided to work more on the topological side. And then I think from there, when you're thinking about like topology and you want a Bn representation on the cohomology, you really want to look at a Z2 orbit configuration space because there's a natural like I'm really thinking about Bn here as the Reith product of Z2 with Sn. And so in general, like if I have a configuration space like this, I'm going to have an action by G Reith Sn. So that's sort of where the Z2 is coming from. But the fact that, so yeah, but I think I also originally tried to start here, which wasn't working. So I think this sort of worked, but yeah, so that, I don't know, did that answer your question?
Yeah, yes, thank you.
And I guess like the recursions actually helped me. So I said that there's recursions that relate these representations, and actually that's a result of looking at a fiber sequence. And so I think that sort of clued me in to thinking about this space here.
Great. Any Per?
So are there combinatorial formulas for how these representations decompose into irreducibles?
No, so this is an open question even like in type A. We have no idea how these like Eulerian representations decompose into irreducibles. We can describe them in terms of plethism. And I think in the Lie case, there's a nice way of understanding it using a major index of Tableau, but that sort of is because Lie overlaps in other contexts. So I think in general, we don't understand these, and we also don't understand these as irreducibles. I think we can also describe them as induced representations. but not interior displacement.
Okay, any other questions? Let's thank the speaker again. Thanks, Sarah. And now the moment that you all came in person for, we'll have a chai break in just a second after Arvind makes some announcements.
Thank you. So I thought it would be prudent to warn you about some of the things. Today seems to be hotter than the week so far. So it is possible. So all these are announcements pertaining to the trip in the afternoon. So it might be hot. The surface of the stone might be hot. So you might want to get socks. You're not allowed to wear shoes, as I told you. Take water with you on the trip. It's about 700 steps. So it's a fair amount of climbing. The plan is to leave. So there'll be 2 buses here outside the main building. They will be here ready to leave by 1:30. The morning session ends at 12:30. So the plan is to run quickly, have a quick wolf down your lunch, and come back here by 1:30. So the driving is 2.5 to 3 hours each way. So the plan is to go 2.5 to 3 hours, depending on traffic. And this is a bus, so it will probably take longer. There'll be 2 buses, so seat yourself in any of the buses. We'll have volunteers, helping you out. Yes, so the plan is to go non-stop on the way, because you would have already had lunch, I suppose. And on the way back, depending on when you leave, we are exploring options for you to have dinner. I am not coming, but there'll be volunteers to help you out if you have any questions. Okay. So if you need to get something from your rooms, this is a good time to go. All right. So let's break. Our things.
Hi, Colin.
Hello.
It's what it's 1:25 in the morning.
Yeah, I'm kind of tired. I
Right.
was like falling asleep like an hour ago. And I was
Yeah.
like, I can't do that.
I think we might be live streaming right now. I'm not even sure. Maybe someone could, if someone's on YouTube. I
Yeah.
don't even know. Yeah. Ah, my goodness. All right. Good stuff.
Yep.
Yep. I'm glad you got the link though.
Yep. Yeah.
Hi, Colin. Can you hear us okay?
Yep.
Great. Do you want to try sharing your screen?
Yep. One sec. All right.
Looks good. So do you want any kind of a warning? We're hoping you'll take 25 minutes and leave 5 for questions.
Yeah, I think that works. I should be good with the timing for myself.
Great. Okay. All right, welcome back everybody to our the second half of the morning session. Our first talk now is on semi-distributive lattices by Colin Defont.
All right, well, thanks. Yeah, thanks everyone for coming, and thanks especially to the organizers for putting this all together and giving me the chance to speak here. So this was based on joint work with Nathan Williams. He was originally going to give the talk, but I'm, I guess, giving it instead. So he's allowed me to give it in his place. So yeah, very frequently I see talks where the speaker starts off by showing a bunch of words in the title and saying, okay, here are a bunch of words, and you probably don't know what they mean. But throughout the talk, I'm going to tell you what they mean. And then at the end of the talk, you'll know what they mean. So here I'm going to kind of do the opposite approach. I have only 2 words in the title. And one of them, you probably already know what it means, which is lattices. And then the other one is semi-distributive. And maybe you don't know what it means because we made it up. But I'm not going to tell you what it means. I'm not actually going to define semi-distributive in the talk. Instead, I'm going to tell you about semi-distributive lattices, but I won't actually tell you what they are because the definition is kind of long. So yeah, that's where we're headed. So I guess I can say at the end of the talk, you'll know what lattices are, but maybe you already do. Okay, so let's start with posets. All the posets in this talk are going to be finite, so don't worry about infinite things. They're all just finite. If I have 2 elements, x and y, in my poset with x less than or equal to y, then the interval between them is just the set of things that are greater than or equal to x and less than or equal to y. So as an example, if this is the Hasse diagram of my poset, then if this is x here and this is y, then the set of red elements is the interval between x and y. And if I have poset P, I can talk about an order ideal, which is just a subset that's closed downward in the sense that if x is less than or equal to y and y is in the order ideal, then that forces x to also be in the order ideal. And I'm going to write J of P for the collection of all order ideals of the poset P. So here's an example in red of an order ideal in this poset. So Nathan and I were coming from the point of view of dynamical algebraic combinatorics, where the goal is to study the dynamics of certain operators acting on interesting sets of combinatorial objects. And one of the most well-studied operators in this area is called row motion. This is acting as a certain bijective operator on the set of order ideals of a fixed finite poset P. One way you can define it is by saying that row motion of I is the set of all x in the poset P such that x is not greater than or equal to y for all maximal elements y in the order ideal I. Okay, so this is kind of a mouthful. But instead, I can break this up into what Tom Roby calls a 3-step waltz procedure. So the 3-step waltz says we start with our order ideal, which looks something like this. The first step in the waltz is to pick out the maximal elements of that order ideal. And if I do that, I get these 3 elements over here that I put in red. Then the second step of the waltz is to saturate upward. And by that, I mean just take the set of things that are greater than or equal to at least one of these maximal elements here. And if I do that, I get this set of red elements over here. And then finally, the third step is just to take the complement. So if I take the complement of this set of red elements, I get this set of red elements over here, which is an order ideal. So this order ideal here is the row motion of the order ideal that I stood with. It's easy to see that this is bijective because you can just retrace your steps through the waltz. And I should also mention that the definition I've given of row motion here might be the inverse of the definition that you've seen before, because I think a lot of people use the inverse of the definition that I've given, but it doesn't really matter for this talk, so don't really worry about it. But anyway, okay, so this is row motion. And one of the goals of our project here was to try to extend row motion to a broader setting beyond what I've defined here. And I'll tell you how to do that using lattices. Okay, so here I am actually going to define one of the words in the title, but not the word that we made up. Okay, so a lattice is a poset. such that any two elements have a greatest lower bound, which is called their meet, and it's denoted by this wedge symbol here. And they also have a least upper bound, which is called their join, and denoted by this V symbol here. Okay, so here's an example of a lattice. You can see if you take any two elements, X and Y, then they have a meet and a join. On the other hand, this over here is not a lattice because, well, for a variety of reasons. For example, if you took the top two elements to be X and Y, then they don't have a meet because, well, I should say a lower bound for X and Y would just be an element that's less than or equal to both of them. And even though they have lower bounds here, they have three lower bounds, they don't have a greatest lower bound. They don't have a lower bound that's bigger than all of the other lower bounds. So they don't have a meet. They also don't have a join because they don't have any upper bounds at all. So really, this fails to be a lattice in many ways. But if you do have a finite lattice, then because the meet and join operations are commutative and associative, it makes sense to take the meet or the join of an entire set of elements. So we can write this symbol here for the meet of all of X, and we can write this here for the join of all of X. And again, that's just the greatest lower bound or the least upper bound. And every lattice, again, every finite lattice has a unique minimal element that I'll denote by 0 hat, and it has a unique maximal element that I'll denote by 1 hat. Now, if you have a lattice, you can define what I call the Fpsac sorting operator. So this is a certain operator that's acting on the lattice. It's just a map that I'll call pop down, goes from L to L. And then there's also this dual Fpsac sorting operator, which is pop up, also from L to L. And these are defined by saying that pop down of X is just the meet of the set of things covered by X. So you look at the things that are right below X in the Hasse diagram of the lattice. You take the meet of all of those, so their greatest lower bound, and this is pop down of X. And then dually, pop up of X is just the join of the set of things that cover X. Except with the caveat that pop down of the bottom element is the bottom element and pop up of the top element is the top element. But other than that, it's defined using these equations here. Okay, the reason this is called Fpsac sorting is because if L is the right weak order on the symmetric group, then you can describe this in terms of basically reversing the descending runs of a permutation, or alternatively, this can be described in terms of pushing numbers in and out of a certain data structure called a Fpsac. I'm not going to be talking about Fpsacs here, but that's basically where the name is coming from. So people had looked at this Fpsac sorting map on the symmetric group from the point of view of enumerative combinatorics coming from permutation patterns. But really, you can do this for any lattice. And I think this kind of deserves more attention in the sense that there are a lot of interesting families of lattices. And for any one of them, you can see if you can understand interesting properties of this Fpsac sorting operator. So for example, I've done this for what are called new Tamari lattices, which are generalizations of Tamari lattices. There are some nice properties there. But there are a lot of other interesting families of lattices too, besides just new Tamari lattices. So here's a picture of what Fpsac sorting is looking like. If this is some lattice, then the red arrows are representing the action of this Fpsac sorting operator. So you can see the top element here goes to the meet of the set of things that are covered by it. So the things covered by it are these two elements here, and their meet is this element down here. And so one of the things you could ask is like, what is the maximal number of steps needed to get to the bottom? Because you can see everything eventually gets to the bottom. And in this case, the maximum number of steps is 3. So this element, for example, takes 1, 2, 3 steps to get down to the bottom. And this is a natural question you could ask for interesting families of lattices. There are other nice questions as well. That's not really what I'm going to be focusing on here. Instead, in this talk, I'm going to be trying to relate Fpsac sorting to a generalization of row motion. But for that, I need to generalize row motion. And so let's start with distributive lattices. So a lattice is called distributive if the meet operation distributes over the join, which is exactly what this is saying here. But this is not how I like to think about distributive lattices. So you can kind of ignore this. I like to think about distributive lattices in terms of what's called Burkhoff's representation theorem. Sometimes this is called the fundamental theorem of finite distributive lattices. And it says that if you take a finite coset P and you look at its collection of order ideals, remember this is J of P, then you can order them by inclusion. And this gives you some bigger poset, which ends up being a distributive lattice. But then also every distributive lattice arises in this way. So really, whenever someone says distributive lattice, in your head, you can think, okay, it's just the lattice of order ideals of some finite poset. But then remember, we have this row motion operator, which is some special bijective operator that's acting on the order ideals of a finite poset by this 3-step waltz procedure. And so you can really think, because of this fundamental theorem of finite distributive lattices, you can say, well, instead of having this act on the order ideals of a finite poset, it's really the same as acting on the elements of a distributive lattice. And this gives us a nice framework for how we can try to generalize row motion, because we can say, well, what if we replace distributive lattices by some broader family of lattices? And well, this had already been done actually in a couple of different settings, namely the semi-distributive lattices and trim lattices. So let me define these briefly. A lattice is called meet semi-distributive if whenever you have two elements A and B with A less than or equal to B, then the set of things whose meet with B is A has a unique maximal element within the lattice. Okay, so what I'm doing here is I'm saying, look at all of the things Z, such that when you take the meet of Z with B, you get down to A. This is going to be some subset of the lattice. And as a subset of the lattice, I want it to have a unique maximal element. And if this is true for any A and B with A less than or equal to B, the lattice is called meet semi-distributive. Then join semi-distributive is really the same as saying that the dual lattice is meet semi-distributive, but you could also say that it's just saying whenever A is less than or equal to B, the set of things whose join with A is B has a unique minimal element. And then finally, a lattice is called semi-distributive if it's both meet semi-distributive and join semi-distributive. And I should say that Emily Barnard has a paper where she shows how to generalize the definition of row motion in a natural way to semi-distributive lattices. Okay, so I should say also that distributive lattices are contained in the set of semi-distributive lattices. So this is really generalizing when you extend it to the semi-distributive lattices. Then there are also these things called trim lattices. So a lattice is called trim if it's extremal and left modular. Okay, so I'm not going to define what this is. Maybe these words are kind of unfamiliar to people, perhaps. But it doesn't really matter for this talk. I'm not really using this definition. In your head, you can just think a trim lattice is kind of like a distributive lattice that doesn't have to be graded in some sense. This is sort of the heuristic idea that Hugh Thomas had in mind when he originally defined trim lattices back in, I think, 2006. So this is some other nice family of lattices. And Hugh Thomas and Nathan Williams have a paper where they show how to generalize the definition of row motion to trim lattices. And this is separate and different from the definition that Emily Barnard gave for semi-distributive lattices. So there are two different ways of generalizing row motion to these different settings. Okay, so Nathan gave a talk about semi-distributive lattices back in the fall, and he had what he calls his A history of lattices, and I thought it was amusing, so I just copied it in here. So he wrote all of this, but he says, okay, lattice theory starts in 1880 when C.S. Peirce shows that all lattices are distributive, and then 10 years later, Schroeder shows that not all lattices are distributive, and then 10 years later, Dedekind defines a lattice. So I guess the discrepancy is because we didn't know, or we didn't have a solid definition of what a lattice is. Dedekind also called these dual grouping because he thought that lattice theory was going to be sort of somehow dual to group theory in some sense. It also says he discovers the number 28. I don't know what that means. You can ask Nathan or something. Okay, anyway, in 1933, Burkhoff establishes lattice theory as a thing. And then in 1939, Dov Tamari is imprisoned for possession of explosives. In 1954 at 8 a.m., I don't know what the day was, but apparently it was at 8 a.m., Orr says, I think lattice theory is played out, which is maybe a little bit depressing. But then in 1972, all lattice theorists moved to Hawaii. And then in 2002, Fomin and Zelevinsky introduced the theory of cluster algebra. So in an attempt to understand some of the combinatorial aspects of cluster algebras, there were these two schools of thought that emerged, one led by Hugh Thomas and the other led by Nathan Reading. So Hugh Thomas is working up here in the realm of trim lattices. And so first he defines trim lattices. He relates them to the representation theory of quivers. He writes this paper with Nathan called Row Motion and Slow Motion. That's the paper where they generalize row motion to the setting of trim lattices. They also have this spin-off paper called Independence Posets. Meanwhile, around the same time, there's Nathan Reading working within the realm of semi-distributive lattices. He defines Cambrian lattices. He defines sortable elements and shards and arc diagrams. It also says, I have dinner with Nathan. That's a little confusing. That's not me. That is Nathan having dinner with Nathan. I have not, oh, okay. I have had dinner now with Nathan Williams, but not Nathan Reading. It also says we play ultimate at Fpsac. So, okay, that's also not me. I still, unfortunately, have not been to a Fpsac in person, although I very much would like to. So sorry about that. But at some point, I hope to be at Fpsac in person, maybe next year. Anyway, oh, I guess also David Spire is in here somehow with Infinity or something. So, okay. Nathan tells me, and I wasn't here for this history stuff, so I'm just taking Nathan's word as a matter of faith here, but maybe it should be taken with a grain of salt. He says, okay, we've got like this bifurcation here in this timeline, and there are these two warring factions. It's like the trim lattices versus the semi-distributive lattices, and they hate each other and they're fighting back and forth, and it's like this epic battle. And the goal of our project, the semi-distrim lattices, is to try to take these two warring factions and sort of unify them into one happy family. So we're trying to be kind of like the peacemakers in this story or something, and give like a unified framework for understanding both the trim lattices and the semi-distributive lattices under one umbrella. And so I guess the punchline is, well, okay, we can do this. So we have a natural way of defining what it means to be a semi-distrim lattice. And okay, I'm not going to tell you what it is because the definition is kind of long and technical and I don't have time to go through it. But if you're interested, I can tell you about it, or Nathan, or you can look at the paper. But I will say, I think we have the right definition because we can actually prove things. So for a while, we were working with this one definition, and it did generalize semi-distributive and trim lattices, but there wasn't really any structure and we couldn't prove any theorems. So then eventually we said, well, let's add this one extra mild condition. And once we added that one extra mild condition, everything kind of fell into place, all the pieces fit together, and then we could start proving a lot of theorems. So this sort of convinced me that we kind of found the correct definition of what it should mean to be a semi-distrim lattice. So one thing we can prove, first of all, is that semi-distributive lattices and trim lattices are actually semi-distrim. So this is not really so obvious from the definition that we give, but it's true and we can prove this. So this means we are actually unifying these warring factions into this one happy family. And we also have this structural result saying that if you take a product of semi-distrim lattices, then the result is still a semi-distrim lattice. And if you take an interval inside of a semi-distrim lattice, then that's also a semi-distrim lattice. So this fact about products is actually not difficult to prove once you have the definition. Basically, you just chase through the pieces of the definition and you kind of verify them. It's a little bit tedious, but it's not difficult. But this fact about intervals is actually pretty non-trivial. So this was really one of the main difficult results of the paper, showing that an interval in a semi-distrim lattice is semi-distrim. So it's not at all obvious from the definition. And we did prove this. And it's also useful once we have it, because it allows us to give these inductive arguments. Basically, we can say, we want to prove something about some semi-distrim lattice. And so we take some elements in our lattice and we look at the smallest interval that contains them. And we say, well, if this is a proper subinterval, then we know by this theorem that it's semi-distrim and it's smaller, so we can apply some kind of inductive hypothesis. But then on the other hand, if this interval is just the whole lattice, that gives us extra structure that we can leverage in some other way to conclude the proof. So that's sort of how a lot of our proofs go. And so it's really useful that we have this closure under taking intervals. That was one of the key properties that we really wanted to be true for these semi-distrim lattices. Okay, so for example, one of the things we can prove with this kind of inductive approach is this fact about poset topology. I'll just remind you that the order complex of a poset is an abstract simplicial complex where the faces are the chains in the poset. And we can show that if you take the order complex of a semi-distrim lattice, the result is either contractible or tomotopy equivalent to a sphere. So this is some nice topological fact about this poset topology. I'm not going to say too much more about this. It's just, okay, this is one thing that we can prove. But then let me also tell you about row motion. Okay, so again, our goal was kind of to generalize row motion to a broader setting. And the fact here is that, well, we can do this for semi-distrim lattices. And maybe this is a little bit unsatisfying because I'm not going to tell you actually how we do it. I will say that in the paper, we do give a very explicit, and I think it's a nice way of actually defining row motion. It's a nice explicit description. I'm just not telling you what it is, just because it would require a lot of definitions and I don't have time to go through those. But the point is we get this natural bijective row motion operator from our semi-distrim lattice to itself. And this definition generalizes the definition that Emily Barnard gave for semi-distributive lattices, and it also generalizes the different definition that Hugh Thomas and Nathan Williams gave for trim lattices. And those were themselves generalizing the definition that we originally had for distributive lattices, which was given in terms of the three-step waltz procedure on order ideals. Okay, so we have row motion, and now we'd like to prove things about it. And so one thing we can prove is that it's actually related in a nice way to this Fpsac sorting operator. So the fact here is that pop down of x, so remember pop down of x is the meat of the set of things covered by x. This ends up being the same as just the meat of x with row motion of x. And dually, pop up of x is the join of x with row motion inverse of x. One reason I like this is because, so Nathan and I had already actually been talking and collaborating on other things. We had done this thing like Fpsac torsing, and then we did something with crystals. And eventually at some point, Nathan realized that like this row motion thing, which was something that he and also Jessica Stryker had named and studied, was very closely related to this Fpsac sorting thing, which I had named. So it's like we had these two separate things that we had named, and then he realized like they're very similar. Actually, he sent me an email. I think the email he sent me said something like pop equals row, and I had to figure out what this meant. And eventually, because I was like, okay, that's not true, but okay. Eventually, I realized that okay, this is what this means. That they are very closely related with this equation here. And you can also say something a little bit stronger. So for any semi-distributive lattice, row motion of x is a maximal element of the set of things whose meet with x is pop down of x. And row motion inverse of x is a minimal element of the set of things whose join with x is pop up of x. So it's a little stronger than saying that row motion of x is in this set. It's actually a maximal element of this set. And this is kind of nice because it gives you an alternative way of thinking about row motion for semi-distributive lattices. Because in a semi-distributive lattice, this set should have a unique maximal element. That's basically the condition of being meet semi-distributive. And so this gives a different way of thinking about row motion for semi-distributive lattices, which is different from what Emily Barnard had given. And this is actually useful. I am using this in a paper that I'm writing with an undergraduate named James Lin to understand special semi-distributive lattices and row motion on them. Okay, so maybe one thing I should say is that I haven't defined semi-distributive lattices or row motion, but if you'd like in your head, you can think about semi-distributive lattices because I have defined those. And you can take this as the definition of semi-distributive or row motion on a semi-distributive lattice, and that makes sense. And the things that I'm going to say on this slide are actually new just for semi-distributive lattices. So if you like, you can just think in terms of those. It's also new for trim lattices. But what this is saying is that if I look at the number of times that row motion goes down, so this is the number of elements x, such that row motion of x is less than or equal to x, that's equal to the size of the image of pop down, which is also equal to the size of the image of pop up. And this is also equal to the number of independent dominating sets in a certain graph associated to the lattice called the Galois graph. I'm not going to say what these things are just for the sake of time. I will point out that this fact here, this equality between the size of the image of pop down and the size of the image of pop up, this is not obvious because this is not true for arbitrary lattices. So really, we are using some structural properties of semi-distributive lattices to prove that this is true. This is also new just for semi-distributive or trim lattices. So I think this is kind of interesting that this pops out here. And then this is also related to a surprisingly boring dynamical system that I call popping up and down. And I don't have so much time, so I'm just going to go through this very quickly. The point is you pick some element z in your lattice. Let's say it's a semi-distributive lattice. We start by doing pop down. So pop down is going to send us to some element that's below it called x1. And now we're going to do pop up. And if you do pop up, you go up to this element that I'll call y1. And you can show that x1 is less than or equal to z and z is less than or equal to y1. And now I want to do pop down again. So if I do pop down again, I go down to this element x2. And then if I do pop up, I go up to this element y2, and I generate this chain basically. And I'm in a finite lattice, so eventually this has to stabilize. And you can ask, well, how long does it take to stabilize? And the answer is it's actually kind of boring. This is maybe a misleading picture. What really happens is this. Basically, after just one step, you're already in the 2 cycle, and then you're just stuck there. So from a dynamical point of view, this is kind of boring because you just do one step and then you're already in a 2 cycle. But I think it's interesting from a lattice theoretic point of view because it's saying that there's structure within the semi-distrim lattices that's forcing the dynamical system to be boring. So it's like interesting lattice theoretically because it's boring dynamically. But anyway, that's popping up and down. And okay, I have like 30 seconds left, so let me just mention a couple of open problems. First of all, you can define a quotient of a lattice in this way, and we have this question of are quotients of semi-distrim lattices semi-distrim? We don't know, but I would love it if someone could resolve this. I think this would be a really nice thing to prove or disprove. We don't know either way. And then we also have this conjecture that basically these conditions here should characterize row motion. Remember, row motion of X has this property that it's a maximal element of this set, and row motion inverse is a minimal element of this set. And we believe that for any semi-distrim lattice, row motion should be the only bijection satisfying these properties for all X. Okay, so that is everything I had to say. Sorry, I went kind of fast at the end, although I was taking over for Nathan, so maybe that is appropriate. But anyway, yeah, that's all.
Thanks, Colin. Questions for Colin?
Yeah, you mentioned distributive lattices can be looked at as order ideals of a finite lattice. Is there a similar thing for semi-distributive lattices?
Oh, yeah. So there's a fairly recent paper called the Fundamental Theorem of Finite Semi-Distributive Lattices. I think that's what it's called. So that's a really nice paper. And it's much more complicated, so I can't describe it right here. But basically, they define essentially what I was calling this Galois graph of a semi-distributive lattice. And then in some sense, they characterize what a Galois graph of a semi-distributive lattice is. So it's a much more complicated version of this Burkhoff's representation theorem.
Okay, thank you.
Mm-hmm.
Hey, great talk. So you mentioned that the definition was really technical. Do you think that you'll be able to come up with either a different definition or a different perspective that would make it a lot simpler? Or do you feel like this is really the right way to talk about it?
I think it's not too bad in the sense that if this talk was 50 minutes, I would give the definition. I think, yeah, well, I'm not so sure. I kind of like the perspective that we have, and it's not so bad once you get used to it. I think I've gotten used to it. So yeah, I think it's not so bad.
Do you know do you have a characterization of when the pop up and pop down applications are inverse by inverse maps? Or in other words, when your up and down algorithm has only 2 elements in its orbits?
So this would basically be kind of like when you don't actually have this extra Z in here. I expect this probably shouldn't happen. I think the reason this, well, maybe in special, trivial cases, it'll happen. But I think the reason this won't happen is because if this were true, pop down would be a bijection. And right, I mean, yeah, because then you'd have this inverse. So, but it's probably not going to be a bijection because oh yeah, I mean, once you have an atom in your lattice, it goes to the bottom, but the bottom also goes to the bottom under pop. So I think once you have 2 elements, it's not going to be a bijection, and so it can't have an inverse.
Okay, thank you.
Any other questions for Colin?
Hi, Colin. Can you hear me?
Sort of, a little.
Oh. I just had a question about when you said the order complex is either contractible or homotopy equivalent to a sphere. What's the
Yes.
dimension of the sphere?
Right. I believe, okay, I've answered this question, I think, every time I've given this talk. I believe the dimension, wait, where did I even have this? Oh, I think it might be something like, maybe, I don't know.
Okay.
Could it be the number, it might be related to the number of coatoms, or I may just not even know. Yeah.
So I'm sorry, I got a little lost in the definition, so I couldn't remember. They're not, are they graded? The semi-distributive, they're not graded, right?
No.
So, okay. So I just wondered what the dimension of the sphere was.
Right. I don't know if I have a way of answering that.
That's okay. I can email you.
Okay.
Thank you.
Any other questions? Well, let's thank Colin again. We expect to see you at one of these soon, Colin. No more excuses.
Okay.
And the next talk will begin momentarily. We're looking for Becky Petrius. Yeah. Becky, can you hear us? Great. We can see you now. Do you want to try sharing your screen?
Yep.
Okay, good. Now we can see your screen fine. So you'll have 25 minutes from when you start and try to leave 5 minutes for questions. Let me know if you want a 2-minute warning or anything.
Yeah, that'd be great.
Okay, no problem. Okay. Our next speaker is Becky Petrius, who will be talking to us on web invariants for non-crossing partitions.
Yeah, thank you. Thank you for coming, and thank you to the organizers. This is work with Oliver Pachenik and Jessica Stryker. What I want to do first is tell you how we came to the question that we ended up answering. So what was our motivation here? All right, so there's a well-known bijection between two-row standard Young tableau and non-crossing matchings, like we see it here. And in this bijection, if I do promotion on my tableau, that's going to correspond to rotation of my matching. If I do evacuation on my tableau, that's going to correspond to some reflection of my matching. And we have a similar thing with 3 rows. So there's a bijection between 3-row standard Young tableau and these objects called SL3 webs. And we have the same properties. So promotion on the tableau corresponds to a rotation of my web, and evacuation on the tableau corresponds to reflection of my web. So what we want to do is change this object over here. So instead of looking at standard Young tableau, we want to look at increasing tableau. So an increasing tableau is strictly increasing in rows and columns. So we have 2 examples here on this slide. These are a K-theoretic analog of standard Young tableau. So they're going to show up when we're looking at K-theory of the Grassmannian as opposed to cohomology of the Grassmannian. We have a lot of the same combinatorics. So we have a K promotion on these tableau and a K evacuation on these tableau. So what we want to do is mimic that same story with standard Young tableau. In 2 rows, things are looking pretty good. So there's a bijection between packed 2-row increasing tableau. So packed just means, for example, here I have every number between 1 and 10. So I'm not missing any entries. And again, if we do this K promotion on our tableau, that's going to correspond to rotation of our non-crossing partition. And if I do evacuation on my tableau, it's going to correspond to a reflection of my non-crossing partition. So that's pretty good. But we're going to run into issues when we move to 3 rows. And the issue is that we don't have an object to biject with. So we have these 3-row increasing tableau. We want some kind of object on this right-hand side to give us a bijection. And one of the motivations for this is, of course, we want promotion on the left to correspond to a rotation on the right, which is going to give us information about the order of promotion on these 3-row increasing tableaus. So that's kind of where we're coming from. This is the question we originally wanted to answer was, well, what kind of object can we make on the right here to give us this nice bijection that's going to work nicely with promotion? So we thought about this for a while and kind of just kept circling around and not getting what we needed. So we thought, let's just take a step back. And maybe we can fill in some other information that will help us. So our idea is, I didn't tell you all of the story with the standard Young tableau. So those objects on the right-hand side, the matchings and the SL3 webs, have some nice polynomials associated to them. And that's not true in our increasing tableau story. So maybe what we need to do is find some polynomials associated to those non-crossing partitions, kind of fill in that part of the story with the 2-row increasing tableau, and maybe that will somehow give us enough information that we can guess what this object is supposed to be on the right-hand side here. So that's the question we're going to talk about today. And I'm going to start by telling you what those polynomials are for the standard Young tableau case. So we're going to talk about the polynomials associated to the matchings. All right, so to start, we have this matrix of indeterminants. And we're looking at polynomials in these variables. So for example, I have this polynomial P13, x1, y3 minus x3, y1. So just any polynomials in our variable set here. And we're going to have a left action of SL2. So I can take any element of SL2, multiply that by my matrix on the left. Of course, I'll get a new matrix. And in my polynomial, I'm going to replace my variable by the corresponding thing. So here, any place I had an x1, I'm going to replace it with an x1 plus 2y1, as we see in my example. And in this particular case, if I simplify that down, I get back the same polynomial that I started with, and this is going to be true for any element of SL2 with this particular polynomial. So we'd say that this polynomial is invariant under this action. We might want to ask which polynomials are invariant under this action. And classical invariant theory will answer that question for us and tell us that the set of the space of invariant polynomials is generated by the 2x2 minor. So this P13 we were looking at is, of course, the 2x2 minor using columns 1 and 3 in our matrix. And in general, we can specify any 2x2 minor by a Pij telling us which 2 columns we're using in our minor. So since these are generators for our space, we might want to think about products of our generators. And we're going to have 2 nice ways to encode the products of our generators. So here I have an example, a product of generators. I'm reminding you that the generators are minors, so that's our second line here. And one way we can encode these generators is by a diagram like we see at the bottom. So I have, for example, a P12 in my product. So I'm going to have an arc between 1 and 2. I have 2 instances of P34, so I have 2 arcs between 3 and 4. Pretty straightforward way to encode our product. We could do it instead using a tableau. So I have the same product of P's on this slide. Here, again, I have a P12, so I'm going to have a column in my tableau of 1, 2. I have 2 instances of P34. So I have 2 columns of 3 and 4. I can force my tableau to be weakly increasing in the first row, but then of course I don't get to control what happens in the second row. So I kind of wild down there, but I have some tableau with weakly increasing first row. Right, so a little review on this slide. So our invariant space is generated by our 2x2 minors. If I have an M-fold product of 2x2 minors, I can encode that using a tableau of shape MM with weakly increasing first row, and just whatever the second row does is what it does. So from there, standard monomial theory is going to tell me that if I just look at semi-standard tableau, this is giving me a linear basis for the degree 2m homogeneous part of my invariant space. So again, the semi-standard tableau are giving me a basis. Right, so let's restrict our space a bit and only think about products where I'm using each index, each column of my matrix exactly once. So here I'm using each column 1 through 14 exactly once in my product. If I restrict to this space, then what do my two objects look like? Well, over here, I have tableau where now each entry is used exactly once. I have a strictly increasing first row, and of course, an uncontrollable second row. And my diagram now is going to be a matching since I'm using each index exactly once. It's going to be potentially crossing. This example is non-crossing, but a potentially crossing matching. So that's the two kinds of objects I'm getting if I restrict to using each column of my matrix of variables exactly once. So what happens then if I want to think about a basis in this restricted space? Well, then my basis consists of the set of standard Young tableau of shape MM and a set of non-crossing matchings. So for example, we can look at if n is 4, I'm looking at two-fold products. I have 3 of those, which I see in the first line, corresponding to these 3 tableau I see in my second line. If I want to think about the basis, I'm looking for the standard Young tableau. So I see that the first guy is in my basis, the second one is in my basis, and the third one is not. And then on the third line, I have the matchings. I can see the first element is a basis element because it's non-crossing. The second one is not, and the third one is. So one thing we can see from this example is that my two bases, my standard Young tableau and my matching basis, are actually distinct bases. They're giving us different polynomials that they correspond to. So since in this third example, in this third line down here, we have this crossing matching that's not a basis element, of course, we should be able to expand it in terms of basis elements, which not at all surprisingly, we could do with a crossing rule. So if I have any kind of crossing in my picture, I can replace it with the sum of these two non-crossing pictures. Probably very familiar to a lot of you. And we have one more piece here. We're going to have an SN action acting on the right. So I can take my matrix of variables and multiply on the right by an element of Sn, and that's going to permute the columns in my matrix. So we have an example of that here. So what's going to happen to my P13? I'm going to replace all the X1s with Xn's, etc. And I'm going to get some other polynomial. So now that we have an Sn action, we've turned our space into an Sn module, which actually turns out to be the spec module SMM. So kind of putting it all together, we have the spec module and we have two bases for it, the basis of non-crossing matchings and the basis of standard Young tableau. We have a similar story in 3 rows. We'll skip the details, but all the stuff proceeds the same way. So if I'm looking at 3-row case, I'm going to have 3 rows of variables. We're looking at an SL3 action on the left and thinking about the invariant polynomials. That's a set of 3 by 3 minors, all the same story. Let's restrict to using each column in our matrix exactly once, and our bases are going to look like 3-row standard Young tableau and the SL3 webs. And again, these are then bases of the spec module SMMM. So the same story in 3 rows. We're kind of focusing on 2 rows here, so we'll just skip those details. All right, so that's the background that we want to fill in for our story. So again, kind of the take-home point from that is if I have any kind of matching, I can easily associate a polynomial. So I'm just going to look at my matching. I see I have 1 and 6 match, so I'm going to have P16 as one of the factors in my polynomial. So I have some nice polynomial associated to my matching that's meaningful and invariant under some action. And this is what we want to recreate for partitions with no singletons. All right, so what do we want? So again, we want to be able to associate a polynomial to any partition with no singleton blocks, so no blocks of size 1. We want a nice SN action on this. So in particular, we want the long cycle to rotate our non-crossing partition. We also want to agree with some previous work of Brendan Rhodes. So Brendan kind of explored this just diagrammatically, not looking at polynomials, just looking at pictures. This is not an equality. And he has these crossing rules that he found. So we want our world to agree with his crossing rules up to sign. So that's kind of our wish list. Let's zoom in on these crossing rules just to notice a couple of things about them. So I want us to notice that the block size changes. Not everything inside of one of our crossing rules has the same block sizes. So let's look at, again, this is a minus sign, not an equality. Let's look at our third rule down here, and let's take each of our vertices literally. So this is A1, A2, A3, B1, B2, B3. And let's look at the block sizes. So in this left-hand guy, I have 2 blocks of size 4. Then I have blocks of size 4, and now I have a block of size 6 and size 2, 5 and 3, 5 and 3. So this is going to be important in our next slide. We see that the block sizes change in our crossing rules, but the number of blocks does not change. So in each of these rules, everything has 2 blocks. We're not going to gain or lose blocks with our crossing rules. Okay, so let's say we're trying to make our polynomials associated to our partitions, and we just want to make a naive guess. So I would claim the most naive thing you could do is just try and directly imitate what we just did. So I have a partition here. I see I have a block composed of 1, 4. So let me take a minor P14. I'm going to take all top justified minors. So I'm using columns 1 and 4 in the first 2 rows. I see I have a block 2, 3, 6, 10. So let me take P 2, 3, 6, 10, where again, I'm using columns 2, 3, 6, 10, and the top 4 rows of my matrix M over here. And then I have my block 5, 7, 8, 9. So I'll take P 5, 7, 8, 9 and look at that product of minors, which is kind of just trying to copy and paste exactly what we did with those matchings. But this is not going to work, and we can see that by looking again at these crossings rules that we're trying to keep true. So notice here I have, let's see, I'm now drawing over myself many times, but I have 2 blocks of size 4 that are crossing each other, the red and green block. So I'll kind of go back to that in the crossing rules. But first, let's notice in my polynomial that I currently have, I'm only using the first 4 rows of variables. So I can really cut this matrix off at x4, 1, x4, 10. So this only uses the first 4 rows of variables. And again, I have these 2 blocks of size 4 that are crossing. So I should be able to use Brendan's crossing rules and uncross those using, again, the third line of our crossing rules. But notice if I do that, I started out with 2 blocks of size 4. I'm going to end up on the right with a block of size 6. And this term is going to use 6 rows of my variables. So we see a problem. We can't have just 4 rows of variables on the left and 6 rows of variables on the right. So I can see that my naive guess of just take upper justified minors corresponding to the blocks is not going to be what we need to do. So we're going to need to be a little more creative than that. And let me show you what we ended up with here. So I'm going to start again with a partition with no singleton blocks. And I want to then create a set of what we call jellyfish tableau. So you can see the set of jellyfish tableau below. Our rules are as follows. So the blocks of my partition are going to be the columns of my tableau. So I have block 1, 4. So each jellyfish tableau has column 1, 4. I have block 2, 3, 6, 10. So I have a column with 2, 3, 6, 10. And I have block 5, 7, 8, 9. So I have a column with 5, 7, 8, 9. Each column is going to have an entry in the first 2 rows. So our first 2 rows are crowded. They're kind of solid up top. And then below that, there's exactly 1 entry in each row. So that's why we're calling this is our jellyfish, because it's supposed to look like a jellyfish. So it's kind of solid on the top, and then it has some kind of tentacles dangling down. So we're going to form that tableau in every way possible. And we see all of those examples here. And each of these jellyfish tableau is going to be corresponding to a product of minors. So let me show you one example of that. So let's take our jellyfish tableau here. Each column is going to correspond to a minor, but we're just going to be creative about which rows of our matrix M we're going to use in our minor. So let's start on the left. So I have this column 2, 3, 6, 10. So that's going to correspond to a minor that uses columns 2, 3, 6, 10. So these are the columns. And the rows that I'm going to use for my minor, 2, 3, 6, 10. The rows I'm going to use for my minor are determined by the rows that my column uses. So my first column here uses rows 1, 2, 3, and 4 in my tableau. So I'm going to use rows 1, 2, 3, and 4. So that's my first minor corresponding to my first column. For my next column, I'm using columns of my matrix M 5, 7, 8, 9. And for the rows of my minor, I'm going to look at which rows are used in that column of my jellyfish tableau. And I see that I'm using rows 1, 2. Whoops. Come back. I'm using rows 1, 2, 5, and 6. And lastly, I have my column 1, 4 in my jellyfish tableau. So this is going to be the minor where I use columns 1 and 4. And my entries are in row 1 and 2. So I'll use rows 1 and 2 in my minor. I also have a sign out front. We have some inversion number. Let's call this T. That's defined how you would guess it would be. So our jellyfish tableau is going to correspond to some sign and then the product of these 3 minors. So what's true about these jellyfish tableau then is that the number of rows that we're using in our polynomial doesn't depend on the block size, it just depends on the number of blocks. So we said that that was okay with those crossing rules that we were trying to keep.
Take about 2 more minutes.
Yeah, perfect. So again, if we have our non-crossing partition or our crossing partition in this case, we're going to form our set of jellyfish tableau and then sum up all the corresponding polynomials for each of those. And that is our polynomial that we're looking for. All right, so our main theorem then is that if we take the non-crossing partitions, they're going to give us a basis. So the non-crossing partitions of 2D plus L into D parts with no singletons is a basis for the spec module SDD 1 to the L. So let me just pause there for a second. So the spec module shape is just what we get if we kind of shake out all the jellyfish and left justify everything. So in this case, we'd be looking at, we're just smushing everything to the left, and that's the spec module that we're talking about. So our non-crossing partitions give a basis for the spec module, and we have a nice action, a nice SN action. So the long cycle is going to rotate our partition, and W naught is going to reflect our partition. Okay, the crux of all of our arguments are our generalized crossing rules. So I'll just show you the picture of them. So these can specialize to Brendan's rules that we are trying to keep, but they're much more general for our purposes. And then lastly, I'm calling them invariant polynomials. What are invariants of what? So I have my matrix of indeterminants, and they're invariant. My polynomials in these variables are invariant under a left action of this subgroup of SLD. So I have a 2x2 block up here, a big block on the bottom, determinant 1. So they're invariant under that action there. And I think that's all that I have to say. So thank you.
Thanks very much. Let's see, where did you go? Can you hear us?
Me?
Yeah.
Yes.
Something went funny with the screen, but that might have been on our end. Are there any questions? Q.
Thanks for the lovely talk, Becky. I was wondering, I remember in Brendan's paper, he has there's some tiny little comment where he says, you could do this other crossing rule or other uncrossing rule. I forget exactly how it works. So, I mean, can you say anything more about why Brendan's rule is exactly the right rule for you to be using?
Not anything very meaningful. It just seemed to work for him, and so we thought maybe it should work for us too. Yeah.
Okay. Thanks.
Other questions? Oh, yeah.
So it seems that many of the tools you use are available also for other types. Have you thought of trying this?
We have not. No, we haven't thought about that at all. So I accidentally skipped my what are we going to do in the future slide. But yeah, we haven't thought about other types. We still want to go back to our 3-row increasing tableau question. That was our original motivation. We want to think more about what we can do with jellyfish tableau, and we want to connect this better to Brendan's work. But other than that, we haven't thought about anything. So we're still
in particular, symplectic case would be natural candidate, right?
Yeah, we haven't thought about that at all.
Okay, thank you.
And is 3-row like the limit for this kind of thing, or do you think 4-row tableau would also be interesting?
So in the standard Young tableau case, the webs get crazy after 3-row. So I think Jessica and Oliver and 2 other co-authors are working on the analog in the standard Young tableau 4-row case. But in general, the web situation isn't what we want it to be in the standard Young tableau 4-row case. And for the increasing tableau, the promotion gets crazy after 3 rows. So we wouldn't expect anything nice, maybe.
Right, right. Now it's interesting how increasing tableau really help make things work in certain situations. So it's good that it does it here too. Yes, there's a question back there.
Do you know if you can translate this into a basis of the top cohomology of the corresponding Springer fiber?
I don't know that. Yeah, I don't know much about that at all. We've started working with Heather Russell to learn more about Springer fiber things, but personally, I don't really speak that language, so I can't say.
Anything else? Oh, let's thank Becky again then. Okay, and Chris, is your name pronounced Bowman or? Oh, wait, well, you're still muted somehow.
Hey, yes, it's Bowman.
Okay, great. Can you try sharing your screen and we'll see?
Yeah.
Awesome. All right, but we're seeing your, yeah, that's better. Good. Now we're just seeing the slides. Awesome. Okay, so our final talk of this morning's session will be by Chris Bowman talking on the work of Christine Bressenrud.
Right. So first of all, thank you very much for the opportunity to speak about Christine with a community that meant a lot to her and that she did a lot of work for. The first time I met Christine was a week of good wine and Kronecker coefficients in Banff. And we wanted to solve a conjecture of Christine's from 1999, which I'm going to tell you about in a little bit. And she had all the big ideas in place before, just on day one. But it took us a year of hard work in order to take care of these intricate details and the case-by-case analysis, which I will not tell you about in this talk. And for me, this was very Christine. On one hand, brilliant and with these big ideas in place, but also this diligent, detail-oriented calculation and hard work. And this hard work and dedication was how Christine approached everything. Running the department in Hanover, her work for the DMV and the European Women in Mathematics, which she co-founded, maybe founded, I can't remember. And she finished the report of her student Adrian's 200-page thesis the week before she passed. So I was at the last pre-COVID conference in Oberwolfach, and Igor Pak said to me that Christine was the only person in the conference that could possibly have understood every talk. And so what I will be talking about today is my own very small view of her work within combinatorial representation theory. And as some of you might know, it would be impossible to discuss all of Christine's work across group theory, Auslander-Ruyten theory, modular representation theory, and algebraic combinatorics. So I've just picked some of the bits that I understand. Okay, so one of the problems that Christine and I worked on a lot together was the Kronecker problem. So I'm going to let Sn denote the symmetric group on n letters. And I'm going to let chi lambda c be one of its irreducible characters labeled by a partition. And the Kronecker problem, which is old and easy to state, but hard to solve, is can we compute the products of these characters? So if you haven't seen it before, let's look at an example. And S3 is the first non-trivial example. So well, here is the character table of the symmetric group on 3 letters. And I am going to calculate the tensor square of this 2-dimensional character here. Okay, well, I'm squaring things. So what do? You just square all the numbers. So 2 times 2 is 4, 0 times 0 is 0, minus 1 squared is 1. And so lo and behold, here we have a tensor square of this character, easy peasy. Now notice that if I sum all the numbers in this column, 1 plus 2 plus 1, I get 4. If I do 1 plus 0 plus minus 1, I get 0. 1 plus minus 1 plus 1 is 1. And so this is the answer to this problem for this question. Namely, take this tensor square. Every single representation appears exactly once. Okay, so high off of that success, let's see if we can understand anything about this problem. No, we can't. It's really hard. It's one of these problems. It started in 1939 to some extent, and it's never really, we haven't got very far in that time. And so part of Christine's work was somehow looking at these impossible problems, and I've shown you one of them, the Kronecker problem, and saying, okay, well, it's impossible. Let's look at milestones of our understanding. And one of the things you can do is classify nice products. And what do I mean by nice here? Well, if a product is irreducible, so A times B is just C, doesn't decompose at all, well, that's nice. Slightly broader class would be homogeneous. So A times B is a scalar times C. And a much harder class, a much more interesting and rich class is multiplicity-free products. And this is one of these questions that appears in a lot of places in a lot of fields. In invariant theory, I believe in invariant theory, it's about commutative endomorphism algebras. In algebraic combinatorics, we find it somehow the limit of what you can know for certain types of question. For example, P-Castan Lustig polynomials, we can calculate the ones, well, okay. We can prove Lustig's conjecture for the ones that are multiplicity free. And in this case, algebraic combinatorial problems like Kronecker and Flepperson coefficients and things like that. So those are the nice products. Another big question that's been coming up recently in this field is, can we detect positivity of coefficients? So this is a complement to the multiplicity-free question. If the first question, multiplicity freeness, was when is A times B a sum of things all appearing with coefficient 1, this question is, so that was throwing away coefficients, being like, I only want 0 or 1 coefficients. This is saying, okay, what if I don't want to know the coefficients? I just want to know if it's non-zero. And then finally, a sort of even harder question is, how do you decompose these products into symmetric and anti-symmetric parts? So let's start with the first question. So tensor product of any representation with a one-dimensional character is always homogeneous and simple. There you go. Here's a product with a trivial character, which, as you know, you can multiply every number by 1, it stays the same. And so this character stays the same. And then, okay, there's also the sign character. And as some of you may know, if you take the sign character, you tensor, what you do is you flip in the east-south axes. Well, okay, the east-southeast axis, if you're English, or a different one if you're French or Russian. So both of these are homogeneous and irreducible and easy, right? And we've already seen in our very first non-trivial example involving the first non-one-dimensional representation of a symmetric group, it's not homogeneous. There's 3 of these things, and it's not irreducible. There are 3 of these things. And in fact, what Christine proved with Sasha Kleshev in 2000 is that these are the only irreducible or homogeneous products for Kronecker coefficients. And this is a similar vein of classification theorem, which Christine pursued in other places. For alternating group characters, so restrict from Sn to An, it's alternating subgroup. These were classified in 2000 again. And products with very few, so here this only has 3 homogeneous components. If you say, okay, I'm not just interested in 1 homogeneous component, but maybe 2 or 3 or 4, these were classified by Bessenroth and Willenberg in 2014. So this is one sort of axis of our understanding of Kronecker coefficients, which is due to Christine, and it's via how many irreducible components appear. Okay, so I said I'd tell you a bit about symmetric and anti-symmetric parts. So take this character, square the character, or square the group element. You can do both these things. If you add them up and half them, we call that the symmetric bit. If you do one minus the other and half that, we call that the anti-symmetric bit. Let's have a little look here. I'm going to show you the symmetric square of the character we just saw. Okay, so it's going to be 2 squared is 4. The square of the identity is itself, so this is 2 squared plus 2 over 2. Okay, now the next one, 0 squared is this guy. The square of the 2 cycle is the identity, so 0 squared plus 2, take half. Okay, here, if I square a 3 cycle, I get another 3 cycle. So if I square this and add it back and take half, what I get is the character 3, 1, 0. And notice that this is the sum over the first 2 rows here. So 1 plus 2 is 3, 1 plus 0 is 1, 1 minus 1 is 0. So there's the symmetric square for you. And we said that the whole, from definition, the tensor square is the sum of the symmetric and the anti-symmetric parts. And so, well, the anti-symmetric bit needs to be everything that we've already seen that wasn't here. Okay, and so in 2022, Christine and I classified the symmetric and anti-symmetric Kronecker products which are homogeneous. So for the symmetric ones, it's pretty boring. But the anti-symmetric ones, you get the boring one where like, okay, the trivial guy. You also get the standard representation, if you like, n minus 1, 1. A couple of small rank things, which always happens with Kronecker coefficients. And that's everything up to conjugation. Okay. So here's the hardest of the Kronecker problems that I have worked on with Christine. And it's about when can you understand these coefficients? So when do we have nice formulas for Kronecker coefficients? Well, there's a very famous one, which appears in Stanley's book, which says, okay, if I take any representation and tensor it with this standard guy, well, that's the same as restricting from rank n to rank n minus 1, inducing back up, oh, and removing one guy that sort of appears extra that I don't like. And so we can do it in terms of addable and removable boxes, like so. So here, this is going to be my lambda. So if I restrict it, I just remove all possible nodes. So here, I remove that node or that node, and so that is the restriction. When I induce that, I'm going to say, okay, how many ways can I add a node to this guy? Well, there's 1, 2 ways I can add a node to this guy. And for this guy, I can add a node in 1, 2, 3, 4 ways. And so I'm going to take this, I'm going to say, aha, well then what is this tensor product? It's just the thing I had there, but I cross out one of the copies of the representation lambda I started with. So here, this is a multiplicity-free product because, okay, everything appears once now that I've crossed out this guy that appeared twice. Okay, so that's one of the nicest character products formulas. But I have another favorite one. So here, oh, that's nice and easy. Everyone knows how to decompose the tensor product with sign representation with itself. It's just the trivial. Okay, easy peasy. What I'm going to do now is fatten out this rectangle by making it go like this. So I'm going to consider KK tensor square. Okay, well, I'm going to fatten out the original guy that I started with. There's his fat friend. I'm going to add something new which couldn't appear before because the first row is would have been too short. And another guy here. Okay, now let's start seeing the pattern. So in the next one, I see, okay, this increasingly long first row guy, he's always going to appear. Now this guy appears by adding to this one in the first row. This one appears by adding to that one in the first row. but we do get some new stuff as always. There you go. I am leading somewhere with this. This is going to stabilize in a way. Okay, so now long first row guy. Let's increase him, increase him, increase that one. That's me adding 2 there. And then a couple of other things that crop up. Cool. I think I'm going to stop there because that's quite enough. But what I'm going to do is going to color things in. So notice that, okay, here, what are these partitions in blue? Well, these are partitions which have all even parts, 4 even parts, in fact. So this is the partition 2, 4, 2, 2, 6, 4, 2, 2 cubed. And indeed, you can sort of see these as just, okay, okay. And then what are the white guys? The white guys are the partitions with exactly 4 odd parts. So notice that, okay, 1 squared didn't appear here because 0 is not odd. Okay, those are the odd ones. And so this is an old thing, but from 2010 or so. But Christine and I recently, and Stembridge also noticed, oh, okay, actually, not only is this already a nice formula for the tensor squares of these gray partitions on the left, but actually the symmetric parts, the symmetric part is all the even guys, the anti-symmetric part is all the odd guys, and so it has a nice decomposition as well. So I said that there would be a classification of these multiplicity-free things. Oh, and I should just point out, notice that everything here appears with coefficient 1. You might not notice that because I didn't write 1s everywhere, but such as things. So what we do is we classify these multiplicity-free products. And the list isn't great, it's a bit ugly. It's got the first example I showed you, fine. The second example I showed you and some variants on it from induction and restriction. Some other guys, okay, a 2-rower and a hook, a rectangle and some small partitions, small depth, and some other things. And the point isn't really what is on this list. The point is for everything on this list, there is a formula which gives you exactly the answer of the Kronecker decomposition. And this is somehow, in one sense, one of these axes of understanding. And it's sort of, in one way, as far as we can push it. You can classify the ones with, I think you can classify the ones where the highest coefficient is 2, rather than here where its highest coefficient is 1. But it doesn't get much further than that. So again, Christine conjectured this in 1999, having done a lot of computer cases. She then did a lot of work over it over the years, and we finally proved this classification in 2016. And it involved 2 lovely ideas that she said, okay, let's set these 2 off against each other. One is de Vere recursion, which allows you to remove little bits from partitions. And the other is the semi-group property, which was quite new then, and it's due to Manavel, which is that you can add partitions and the Kronecker coefficients must increase. And that's a really lovely property. But what I wanted to stress here was, okay, this is a very hard and in some ways ugly classification, which involves a lot of work and a lot of detailed calculation, as well as the big ideas. And this to me is a very Christine sort of theorem, this complement of big ideas, but also incredibly hard, detailed work. And indeed, I said it was a very Christine theorem. Here are some other ones by Christine. So, oh, not the first one. So Stembridge in around 2000, the same time that Christine made the conjecture, looked at symmetric functions and Kac-Moody generalizations. Christine did the spin symmetric functions, the quasi-symmetric functions with Willigenberg, and recently with myself and Rowena Paget, the plethism products of Schur functions. And in Adrian's thesis, 200 pages, remember, Adrian Homer did the products for alternating groups, which is incredibly difficult. So yes, this is a big theme of Christine's work. These, how far can you push a question? How far can you push your understanding? And one of the answers is that multiplicity freeness gives you a way of getting a grip on these otherwise intractable problems. For example, the Plethism products are one of the other one from this talk of Stanley's big problems in algebraic combinatorics. So impossible in general can be solved for multiplicity-free things. Okay, so multiplicity freeness is over now. We're going to look a bit at positivity. So here is a very famous theorem of Burnside, which says, okay, given any faithful character of any group, if you take enough tensor powers of it, you will eventually see every character of the group, which is lovely. And a good question there would be, okay, I haven't got time to tensor this off to infinity. How small can M be? Well, we've already seen that if I take this little staircase partition here, 2, 1, and take its tensor square, I see everything straight away. M is 2 here. And what Jan Saxel conjectured is that if I take a triangular number and I take the staircase partition, k minus 1, k minus 2, k minus 3, 2, 1, this sort of thing that looks like a triangle, this triangular number, his tensor square contains every symmetric group character. So M is 2 is the conjecture. And this has proven to be another one of these milestones in the theory. It's attracted a lot of attention, but seems bizarrely out of reach, even though it's just take this tensor product, this guy times himself, decompose him. You're like, okay, that's just one partition. So row, row, lambda for row this staircase. And we can't do it. And all we actually need to do is detect positivity. And it's somehow, it shows just how hard the Kronecker problem is. And this is a question that really captured Christine's imagination, and she's proposed a lot of generalizations of this conjecture and made a lot of headway on it. And one of the most interesting generalizations she did with Greta Panova, which said, okay, actually, this is very specific. Lots and lots of these guys exist, and they say what they should look like. And this will appear in a paper of Greta's in the summer, I think. So I'm going to come back to that. I haven't really proven anything in this slide, but I'm going to prove something in the next bit. So I said part 1 was about algebraic combinatorics. This is a field that she worked very hard in. Part 2 is about modular representation theory, a separate field, which may not be that popular with the audience, but I'm going to show you how Christine used the ideas from modular representation theory to understand these Kronecker coefficients, which hopefully people do like. So here's a nice example of using 2 modular representation theory in order to understand the Kronecker problem. So here's the statement, very cute. Every symmetric group character of odd degree appears in Saxel's tensor square. Huzzah! So here's an interesting, well, barely interesting little tensor square here, the first staircase that isn't just the one that we looked at earlier. Here are the Kronecker constituents, and I'll go as far as that. Okay, there we go. Everything else is a conjugate, so that's preserved because this is a self-conjugate partition. So this and all its conjugates appearing with the same numbers. So here's the tensor square. Which one of these have odd degree? Well, these 4 have odd degree. These guys are even, but in fact, there's an even more general thing which works because of this nice idea in 2 modular rep theory of character being as odd as possible within its 2 block. And that's called height 0. And okay, this last one is height 0. So here we get everything apart from this guy. He's of oddish degree.
Chris, you know you have about 4 minutes left.
Okay, cool.
Yeah.
And I just wanted to say that, oh, there's this lovely application of this, which came out last week by Harman and Reiber. They actually proved that the tensor cube, so M is 3, is an upper bound by using these modular representation theory ideas. Cool. And then all I want to say here, because I'm running out of time, is that Christine classified, well, no, Christine didn't classify. Christine almost classified the modular representations there when they had were irreducible. And that this was been recently completed by Lucia Marotti, who, like me, also owes a great deal to Christine. So this is another part of Christine's legacy. And it's been very important in group theory due to work of Kleshev, Marotti, and Tiepp. And Christine really set Lucia on this path. So I just wanted to point out that. So finally, I wanted to end on a conjecture of Christine. So here we go. Character vanishing. Here's another combinatorial question. You can start with, do products factorize uniquely? So if I take a product of symmetric group characters and another product of symmetric group characters, what if they are just the same? Does this imply that the characters you started with were the same? Modulo silliness, like permuting lambda and mu. For Lie groups, the answer is yes. This was a Annals paper by, I can't remember the name of the guy, but the answer is yes. And for symmetric groups, this was asked by Cedric Lecouve, and I was like, oh, great, maybe I'll get an Annals paper proving this. But Christine found counterexamples using the idea of character vanishing. And so we were like, okay, well, let's go into character vanishing. So we started asking, when do characters vanish? What are the elements on which a character vanishes? When is it 0? And Christine used this to solve some of Saxel's constituents. And it's also important in modular rep theory, so it's appeared a lot of other places. So I'm going to let V lambda denote the set of group elements upon which the character vanishes. Does knowing V lambda determine the representation I started with? And the answer is yes. So here is the table S6, and what I've done here is highlight all the zeros. So here, this character vanishing set, so if I take the character vanishing set to be this pair of zeros here, I color in the 2 columns, put these zeros in, lo and behold, the only things where the character vanishing set is these 2 columns is this guy and his friend, linear twist. Again, here is a character vanishing set. For this guy, it's just this column. And lo and behold, when I highlight this column, these are the only 2 rows which have it as its vanishing set. Finally, this vanishing set for this partition is this guy. And lo and behold, only one self-conjugate now partition has this vanishing set. So for symmetric groups, yes, knowing this determines the characters. But we were late to that party too, so this was already solved in 2004. And what I wanted to end it on, and so I'll just state this, it's not very attractive. It's something that says, okay, can we determine when do 2 characters have the same vanishing set? The answer is almost never for the alternating groups, sorry. When do 2 alternating group characters have the same vanishing set? The answer is almost never, unless you're in a very couple of very specific cases involving 3 core and 3 quotient combinatorics of partitions. So this is just a conjecture of Christine's that I wanted to state, regardless of what the details are. It's that almost always character vanishing for alternating groups does determine the character, with some very few exceptions. Okay, thank you very much.
Thank you. Are there questions for Chris?
Chris, have you looked at tensor power? So you have the Saxel conjecture where you have tensor powers of the staircase. Now that should decompose according to, so if you take the d tensor product, then that would decompose according to partitions of D, right? I mean, generalizing the symmetric and anti-symmetric part. Has anybody tried to look at how those different pieces would?
Not yet, no, because it's so hard. So it's somehow doing the symmetric and anti-symmetric things adds another layer of difficulty. It makes it worse. And basically, no, very little is known.
But the symmetric and anti-symmetric, you seem to know, right? Just for staircases?
No, we knew the symmetric and anti-symmetric for the partition 2-1.
So even that's not.
And for the partition KK. And there's some few other instances, partitions of small Durfee size, things like that. But
not for staircases.
Not in general, no.
Thanks.
Other questions? Okay, well, could I have a reference for Burnside's theorem, says Bruce Westerbury.
It's in his book. So yeah, that's in Burnside's book. I don't know where.
Okay. Let's thanks again for a great talk about Christine's work. Yeah. And now a word from our sponsor.
Okay, so the buses are here. So we'll go for lunch, and the buses are basically behind this building. So when we come back from the main guest house, keep walking straight beyond this building. You'll see two white 50-seater buses. Pick one, and please try to be there by 1:30. The sooner we can leave, the more time you can spend, and the sooner we can return. You can return. Shivani, please stand up. So this is Shivani. If those of you who are interested in the trip to Hampi over the weekend, please contact her by today, preferably over lunch. She has contacted some travel agents to help to help plan the details, and she'll let you know the prices and things like that. Okay, so let's hurry. Thank you. See you tomorrow.